Puedes aprovechar que estás aquí e ir al Wells Fargo.
Mira que se acabe esto. Y puedo hacer eso.
Okay. Can people
Very
hear
good
me?
morning, Dave. Yes, we can, Dave. Thanks for joining. Just waiting for a few more seconds and we should get started.
Guess it's okay. All right. So I can start this.
Are you trying to do a quick screen share, Dave?
Yeah. It's this tricky thing about the voice going with the tab. And so I just go. All right, let me do that again. I just want to make sure I'm supposed to talk for 30 minutes and then 15 minutes of questions. Is that right?
That is correct. And your slides are coming through. I will be taking over the screen share just for 2-3 minutes for the
Okay.
logistics.
Should I stop sharing then?
Yes, please. That will be helpful. Thanks.
Okay.
Great. Thank you. We have 2 more minutes on the clock. Let's wait for it.
Oh, thank you, son. Tell mommy thank you so much.
Thank you so much.
If folks on the call, the non-speakers, if they could please mute their microphones and turn off their webcams just to limit shared network bandwidth, that would be helpful. Thanks. Okay, so let's get started. Good morning, good evening, good afternoon, everyone. Thank you so much for joining. Welcome to the 13th annual workshop on the Energy Efficient HPC Working Group. On behalf of Torsten and I, we welcome you all. This is really going to be an exciting event. It's a 2-day event, as a reminder, folks. The workshop event website should be in your meeting invite, and the link is right here. The website includes the agendas, an overview of the speakers and the overall layout of the next 2 days. If others on the call could please mute themselves, thank you. Okay, and just to reiterate, as always, event time question and answers for the speakers or specific questions during the panel sessions. We encourage you all to please keep typing them in the Zoom chat box. And then I request the moderators of each session to please keep an eye on those questions and then discuss them as time permits. Okay, and a very quick overview of the agenda here. We have a keynote, invited talk, really exciting talks coming up. We have a panel on sustainability and liquid cooling. And then tomorrow, I have the order here a bit reversed. So a reminder that first, when you step into the call, there will be a quick 5-minute aggregation where we will come up and touch base. And then in a few minutes, we will break out into different sessions based on your interest, right? So there are 4 main breakout rooms that we have planned for tomorrow: liquid cooling, sustainability, energy efficient software, and operational data analytics. And based on your interest, using the Zoom, existing Zoom controls, right, we should be able to split into one of these meeting rooms. And with that, let us commence. Again, a very warm welcome, Dave, Dr. Patterson. Really an honor to have you here. For folks on the call, Dr. Patterson received his BA, MS, and PhD degrees from UCLA. He is a UC Berkeley Purdy Professor Emeritus, a Google Distinguished Engineer, the RIOS Laboratory Director, and the RISC-V International Vice Chair, right? His most influential Berkeley projects, to say the least, is the RISC and the RAID projects. He received service awards for his roles as the ACM President, Berkeley Computer Science Division Chair, and the CRA Chair, and awards for his teaching. The most prominent book, of course, I grew up reading from this book, really, Computer Architecture, A Quantitative Approach, which he co-authored with John Hennessy, and shared the 2017 ACM AM Turing Award, the 2021 BBVA Foundation Frontiers of Knowledge Award, and the 2022 NAE Charles Stark Draper Prize for Engineering. Thank you so much, Dr. Patterson, for joining this call. The talk title is A Decade of Machine Learning Accelerators, Lessons Learned and Carbon Footprint. Over to you, Dr. Patterson.
Okay, great. Let me share my screen. All right, you can see the screen?
Yes, we can.
Okay, great. I'll take about 30 minutes before questions, and the talk is actually based on these 3 papers, all of which is available. So if you're interested, you can go in more depth. So I'll introduce the TPU family. Just in the time allotted, just a couple of the 10 lessons we'll go over. And the meat of the talk will be about the impact of carbon emissions from machine learning. Go over some of the kind of startling claims out there about what's going to happen, what we learned, and then our conclusions, recommendations, and I look forward to the Q&A. So how did this get started, TPUs? Almost 10 years ago, Google was one of the earlier adopters of the deep neural networks. And Jeff Dean, and he did a calculation on the back of the envelope that said, wow, if one of our apps takes off and 100 million users tries to do translation 3 minutes a day using standard CPUs, Google would have to double all of their data centers to handle that load. So that was, that would take forever and be expensive. So that's pretty scary. So they decided to do a custom, what we would call today, domain-specific architecture of deep neural networks. And the target was to reduce the total cost of ownership for the inference by a factor of 10. So I think maybe by now most people know about this, but there's 2 phases for deep neural networks. There's the training phase where you learn the parameters, and the inference phase where you put it into production, also called serving. And they had to be compatible with existing hardware. So they started the project a year later, hired the people, put them on board. And in a remarkably 15 months, they did everything from invent the architecture and the software stack, fab the chip, deploy it in data centers, which is startling today. So we subsequently published a paper to see how well they did, and they exceeded their goals. Compared to the contemporary machines when this was done in 2015, by being domain specific, they had huge advantages. The performance per watt was 80 over CPUs and 30 over GPUs. So remarkably, in retrospect, Google decided to brag about what they did. So in 2016, at an annual event that's held in May called Google I/O, the new CEO of Google announced the TPU. So I don't know if this is going to, I'll try playing this, but I don't know if this is going to work or not. But let's give it a shot.
And by the way, when you use Google Cloud Platform,
can you hear that?
You not only get access to the great software
Yes,
we
you
use
can.
internally,
Yep.
you get access to specialized hardware we build internally. And talking about that, for machine learning, the scale at which we need to do computing is incredible. And so we have started building specialized custom hardware. We call these tensor processing units, or TPUs. TPUs deliver an order of magnitude higher performance per watt than all commercially available GPUs and FPGAs. And when you use the Google Cloud Platform, you can take advantage of TPUs as well.
So what was the reaction to that? It was kind of a Steve Jobs kind of moment here. Well, if you know your history, this is a picture of Helen of Troy, and the war was fought to get Helen back. So there was a poem that said that Helen was the face that launched 1,000 ships. And I'm thinking of what the TPU was as launching 1,000 chips. So Intel was caught flat-footed. They hadn't been thinking about, they had no idea that machine learning was an interesting big workload. So they started buying companies, Nirvana, Movidius, Mobileye, and Nirvana didn't work out. So later they bought Habana. So that was billions of dollars. Intel's competitors in hyperscalers like Alibaba and Amazon started building their own inference chips that were announced a few years later. And then the venture community jumped in. It actually spent, it says 2 billion here, but spent about $3 billion per year in investments. And kind of every architecture idea that didn't work in the past for general purpose CPUs was resuscitated, and the fact that it might work for machine learning. And we're trying to figure out how that's going right now. So 2016, we announced that we've been building TPUs, and so far they've announced 4 generations. Well, depending how you have 4 or 5 generations. So 2 of them are for inference, TPU v1 and TPU v4. Google just renamed that as TPU v4 Lite, and you can see the technologies and the you know, kind of the peak flops. This is 16-bit flops that we're using, bfloat 16, and then 3 that were aimed at inference and training. And for the inference and training, we built supercomputers out of them. You know, it went from, the first one had 256 chips, and the most recent has 4,096 chips. So what are the lessons we learned? And here are the 10 lessons. I'm going to go over 3 of them. So half of them are just about DNNs, which might not be the focus of this meeting, but half of them are about hardware, which I think applies to supercomputers as well. I'll talk about how fast the DNNs are growing, and then how important memory accesses are, and then how fast has the technology changed for logic and wires. So the models grow incredibly fast. It's a fast-moving field, and the models are growing quickly. So we looked at 2 papers we did 4 years apart, and for inference, it grew almost 50% per year in both memory capacity and floating point operations. So if you think about, it takes at least a year to design and at least a year to deploy, and it's in service for at least 3 years. Over that same time period, the models will grow a factor of 8. That was for inference. At the cutting edge of training, which is very much like supercomputing applications, this is, you know, 1,000 computers computing for weeks. At the bleeding edge, people pushing the state of the art, it's going incredibly fast, almost a factor of 10 per year in terms of how much computation. I'll mention GPT-3 recently. It came out in 2020, but it got tremendous attention. And the big idea of GPT-3 was big. It's the successor was, you know, the predecessor was GPT-2. It went from 1.5 billion of these parameters to 175, so up a factor of 100, and it could do pretty impressive things that got the attention of the whole community. Okay, so that was one of the lessons for deep neural networks. Now for the kind of the architecture hardware, paraphrasing Bill Clinton's campaign of when he was elected, it's the economy stupid, it's the memory stupid. Modern chips, as many people here know, aren't limited by transistors, but by the energy and power that dissipated. So one of the interesting insights that Mark Horowitz made a while ago was that an external memory access going to DRAM is about 100 times the energy of going to on-chip memory or SRAM. And external DRAM access is about 5,000 to 10,000 times the energy of an arithmetic operation. So the consequences of that insight, when we got into deep learning, well, let's put a lot of multiply accumulate units on these. So on the order of 100,000 multiply accumulate units on it. And which is pretty easy to do because it's doing matrix multiply, kind of an ideal thing to do, but that kind of does the energy balance, and that's being done. The second thing is we looked at over time. Mark Horowitz made his statement on 45 nanometer on this slide, and we updated it to 7 nanometer, and we looked at how much improvement there was in the picojoules per operation. And basically, the logic improved the fastest. So in the latest technology, the logic is still getting better. That's improving faster than the wires and the SRAM, and the DRAM is kind of improving the least. So what Google did with these lessons, here are pictures of several generations. The board, individual boards on the top, and it went from, you know, very low power air-cooled to pretty hotter ones with tall heat sinks to liquid cooled across the generations, and the number of chips in the rack are shown there. And TPU v4, this shows the generations, and one of the key insights for the matrix multiply unit is to use systolic arrays, and so that's where the kind of the heart of the TPU is, where all the flops come from. And the first one had a single one that was 256 by 256. That was only for integer. The second was 128 floating point. And then the number of MXUs per core doubled with each generation. And it doesn't use that much, die size, interestingly enough, because of the rapid improvement of logic. Okay. So just looking at those lessons, what did they do to keep up with the growth in compute and demand? Each generation, there was kind of 4 times as many chips per pod in their supercomputer, about doubling the performance per chip per generation, and doubling the memory capacity per chip. As I said, has on the order of 100,000 multiply accumulate units to amortize that energy, and they would double per core per generation to take track of the technology. Okay, so that was the quick 10 lessons. Let me now get into the carbon impact of machine learning, which is what the TPUs are trying to accelerate. Well, there have been some startling predictions about what's going to happen in machine learning that certainly got a lot of people's attention, which I'm calling Malthusian. So this is, you know, from the October issue, almost 9 months ago, of IEEE Spectrum, and a paper in there said the following, that's a quote. They said, let's look at as kind of a standard operation. Suppose we wanted to do enough training to cut the error rate in half to improve the quality. Their estimate was $100 billion and as much carbon emissions as the city of New York. That's what they thought, and that would happen just a couple of years. Well, that's pretty shocking, but that was topped just 3 months later by this report that extrapolated another couple of years, and they said the training of the model, a particular model, would cost more than the total gross domestic product of the United States, which I had to look up, $20 trillion. So not $100 billion, but $20 trillion. So man, if that's true, look, imagine the carbon emissions of spending that $20 trillion to train one model, right? That's pretty crazy. So what this reminds me of is this XKCD cartoon, where he decided to plot the popularity of the world's sustainable in English text and using Google Ngrams. So he plotted the data over time, and he put it on this log-log scale and just drew a straight line on the log-log scale. And so what he said, well, 15 years from now, the word sustainable would appear once per page of English text. 40 years from now, it'd appear once per sentence. And then 90 years from now, all English text would just be the word sustainable. So his bottom line is the word sustainable is unsustainable, but maybe it points out the dangers of just extrapolating, assuming no changes are made. So let me go on here. So how do we document energy use in CO2? It's pretty straightforward. You know, how many processors are you using and how many hours to train? And hours is the right unit for machine learning training. At least hours, if not weeks. Then you calculate the average power per processor. You can do what we did, was measure it. That's the best thing to do. our papers showed for 2 generations of TPUs and GPUs that the average and standard deviations were pretty stable. So you could use ours instead, but it'd be best to measure it. And then there's this PUE factor. Now PUE, probably a lot of you people here know, is the industry standard way we measure kind of energy, how efficient you deliver energy. It's power usage effectiveness, and the overhead that's kind of, you know, wasted from a kind of a computer perspective, that is, it goes into cooling or it goes into power distribution, that doesn't get to the computer. So if it's the overhead is 50%, the PUE would be 1.5. Okay, but multiply that together, and that's how much energy you use. How do you turn that into carbon emissions? Well, you just multiply this parameter of the tons of carbon dioxide equivalent emissions, which includes the greenhouse gases, per kilowatt hour. That's something you can have times the kilowatt hours, and you get how many tons of carbon emissions do you get. Now, where do you get that? You can ask your data center operator. Google happens to publish both the PUE and the percentage of carbon-free energy, which is pretty close to what you want. Okay, so now we get into what we learned, which we call the 4 M's of energy efficiency. So remarkably, if machine learning people are careful, you can reduce, not increase, reduce your energy by a factor of 100 and your carbon emissions by a factor of 1,000. So let me show you that in an example. So what we call this is the 4 M's. The first M is the model. This is basically like kind of the software, the model that you're calculating. So the original, one of a very popular model is called Transformer. It was announced in 2017. And what we're doing is comparing that model in 2017 to the average data center with the average kind of clean energy using the GPU of that era, compared to the new model called Primer. It was discovered by using what's called neural architecture search to be just as good a quality as Transformer, but much more efficient. In fact, it's a factor of 4. So the first M, you reduce your energy and carbon emissions by a factor of 4 by just using a more efficient model. You can kind of think of it as just using more efficient software, a more efficient algorithm. The second one is near and dear to my heart, is the machine, the hardware, the second M. So Google's latest TPU compared to the P100 GPU, which was really not optimized for ML, is a factor of 14 better. So you multiply that together and we've reduced the energy and carbon emissions by a factor of 57. The third M, which is a little bit of a stretch, is about the data center PUE, which we call mechanization. So Google and most cloud companies have very low PUE, like 10% overhead, whereas the average data center average is about 60%. So you get this factor of 1.4 for the third M. And the final M, and this was the biggest surprise to me from this study, is MAP, which is the geographic location. So it turns out even within the same country, it's certainly worldwide, depending where you do your computation, the carbon, the kind of cleanliness of the energy supply varies by quite a bit. But even within the United States, within one country, it can vary by up to the factors of 9. And that's what it was over the 9 years. So in 4 years, it didn't get, 1,000 times worse. It got 1,000 times better, 747 times better. Okay, so that was one study. What about, these excitement about these giant models like GPT-3? So this is a second study to see what happened. So 18 months after the GPT-3 hit the news, Google announced what they call GLAM, which has better accuracy than GPT-3. So at the same S. So before we're trying to match quality, this is trying to improve it. Well, how do they do that? Well, they have 7 times as many parameters. So it went from, a remarkable 175 billion to more than 1 trillion parameters. So this factor of 7 increase that they did. Well, that seems like that just makes things worse, but it's what's called a mixture of experts model, which is sparse. So they only activate 8% of the tokens on 8% of the parameters on any token, whereas the dense models like GPT-3 activates all 175 billion on each token. So that what that means is there's basically a factor of 3 reduction in time and in energy by being sparse. And then while GPT-3 was trained at Microsoft, and it had good PUE, but the energy cleanliness was just the average. So we got another big factor there, another factor. So it's a factor of 14 reduction. So a year and a half later after GPT-3, it didn't get much worse. It got 14 times better in the carbon emissions. This was again by kind of following these 4 amps. Okay, so I've given versions of this talk a bunch of times, and one of the questions I got, well, how much energy does Google use on machine learning? And so we tried to figure that out. And so what we looked at was the same week in April in we first did it in 2021, and we looked when we looked backwards for the prior 2 years to see what it was. Well, this was kind of easy to do because virtually all training and most inference is either on TPU hardware or GPU hardware, and we can tell when it's using it for inference versus training. But there still is inference being run on the CPU, but fortunately, Google has this thing called Google-wide profiling, which keeps tracks of all the routines that you use and how much time you spend on them, and it's a historical record. So we could look back over time and add the CPU pieces for inference. So to our surprise, remarkably, for the past 3 years, every year, it's been less than between 10 and 15% for the last 3 years. Now, Google's overall energy use increased each year with the increased number of customers. So the pie's getting bigger, but the slices of the pie stayed the same. And for those of you who are interested, the split was kind of 3/5 inference and 2/5 for training. Now, when we kind of started sharing that results, there was the Stanford grad students who said, well, I don't want to go in machine learning if it's less than 15% of the work going on. That sounds kind of trivial. So we double checked our data and like, wait, it's 70 to 80% of the flops at Google, but it's only 10 to 15% of the energy. Now, how's that possible? How could it be? Well, we showed you that, right? It's the energy is in the memory, not the flops, and the logic's getting a lot better. So hardware can deliver, especially for matrix multiply, a lot of flops pretty energy efficiently. But this is an example that the domain specific architecture paying off. If we were doing this with CPUs, presumably it'd be 70, 80% of flop, 70, 80% of the energy. All right, this next one, let me go to, yeah, let me see if I can do that. Okay, let me try this as introduction. So what I'm going to do now is talk about these predictions that people have made that I kind of previewed earlier about. It looks pretty bad for ML. So what's a little awkward right now is I'm the Turing Award winner, old timer, and I'm going to be finding flaws in work of younger people. So it's a little bit, it's impolite, right? It's to find, but climate change is really important. So we got to get the numbers right. So even if it's impolite, I think I need to point out that there's some flaws in some of these predictions. So we get the numbers right. So we work on the right problem. Okay, so with that introduction, let me go ahead. First of all, it certainly made sense to raise these concerns about what are the carbon emissions, given all of the computing that's on there. It was great that happened, that we raised the concerns. So the Google paper that found one of those models, I talked about going to primer, but the first step was going to evolve transformer. It did what's called neural architecture search, which is using machine learning or using search techniques to find a more efficient model. So a paper at the University of Massachusetts decided to try to estimate what the emissions were for that neural architecture search. Since the Google paper didn't publish that, they tried to estimate it on their own. And this is a very popular paper. It says it's been cited more than 1,000 times, but that was written a few months ago. I just checked recently, and it's 1,300 times now. Now, because the Google people didn't publish their data, they used what they had. They used the P100 GPU, and they used averages rather than the Google data centers. So if we factor those differences in, that would explain by a factor of 5. Google because using the TPU, you know, 2 of the M's or 3, we're just doing the energy, so 2 of the M's. The machine and mechanization, that was too high by a factor of 5, which is certainly understandable because they weren't using what Google was using. The problem was they also didn't understand one of the subtle things about the search. They assumed the search was done by just using the full-size model, using all kinds of different parameters to search the space. But that's very expensive and inefficient. So it was subtly described in the paper. But they're used instead a small proxy, so a much smaller model to search the space. And then when they found an interesting area, they would use the full-size training. So that meant the estimate was off by another factor of 19. So it was a factor of 88 too high. Now, I said this paper was widely cited. Unfortunately, some of these papers got confused about what this AMIR study was about. It was about the neural architecture search, not about the final model that was trained. They thought it was the training of the model of evolved transformer was what this cost was, which we know now is a factor of 88 too high. These neural architecture searches aren't done every time you use it. They're done occasionally, and then the models are put to open source for people to download. And the downside of this confusion was that there's the training emissions are searching for something, searching for the new model is like 1,000 times the emissions of the final model that was trained, and on that order of magnitude. Okay, so here's, because of it was off on 88, and then they got it off by another factor of 1,000. These numbers on this slide were very widely quoted in technical papers and in newspapers. So training evolved transformer took 2 million GPU hours, cost millions of dollars, in the carbon emissions was 5 times the lifetime of a car. That one hit the press. So this is what the real numbers are. And I showed them on this log scale here. It wasn't 2 million GPU hours, it was 120 TPU hours. It wasn't millions of dollars, it was $40, you know, and it wasn't 5 times the car emissions, it was a factor of 120,000 less. So how big is a factor of 120,000? It's as if you said, I wonder how much carbon emissions is for the average car trip. And instead of calculating that, you calculated, well, what's the carbon emissions from manufacturing a car, and you took that number and you multiply it by 100. That's almost how big this gap is here. So let me go to my recommendations and then open up for questions. So we're going to go over these 4 M's. So ML researchers, if we want to reduce carbon emissions, keep developing those efficient models that can make these factors of 2 to 4. One of the challenges is to reduce the cost of both training and inference of these giant models like GPT-3 and GLAM. My advice is, you know, focus on the kind of the tradition is to try and reduce flops. That's not the right thing to focus on. It'd be focused on memory accesses. It's also important for these researchers to publish energy consumption and carbon footprint to, you know, foster competition based on quality, and to make sure you get the numbers right, because, you know, we documented external estimates for off giant factors. So that's the first, you know. The second one, machine, keep building faster hardware like newer GPUs and newer GPUs or other people's custom hardware. These factors of 2 to 4 every generation. One of the challenges is supporting sparsity with these systolic arrays that are popular there. That's an interesting opportunity. And I've been talking about operational costs, called so-called scope 2. I think life cycle costs are really interesting, much harder thing to calculate, but it'd be a good thing to work on. The mechanization already, we're within, modern data centers can be within 10% of energy waste. So that's about as good as you can get. You can only get a little bit better than that, but use best principles. But publish it so we can have a competition there. And then the map. My big surprise is how much the location mattered. And so use the greenest data center, which today is often in the cloud, but can be very big factor factors there. Google, it publishes its, it has two locations in Europe and 3 in the US that are about 90% carbon-free energy. You can train anywhere. Inference needs to be maybe near people, but training can be isolated. So if it can, why not train in the place with the greenest energy? And so I think, from the machine learning perspective, despite the kind of worrisome articles that are out there, if we keep optimizing these 4Ms, we can deliver on this amazing potential of ML to help in a sustainable manner. And I think I'll do the next slide. I'm just reporting the work about the TPUs that's done by a lot of people here. And as you saw in the first slide, there's lots of papers you could follow up. And with that, I'm open for questions.
Thank you so very much, Dave. Fantastic talk. Folks on the call, please feel free to chime in. Questions in the Zoom chat box would be preferred. Okay, question number 1. Did you use machine learning for PUE improvement?
Google has been publishing its PUE for a long time, and so it didn't need to do that. There is a paper that the people at DeepMind, which is one of the Google companies, talked about using ML to try and optimize it. But no, just kind of standard practices can get the PUE down to 10%. Maybe if you use machine learning, you can make it a little bit more efficient than that. But we didn't have to do that.
Okay.
All right. Maybe I should look at the
question number 2. Or I could read them out, Dave. So question number 2. How do you think machine learning accelerators should be integrated in a system? All in one rack, as in disaggregated, or one machine learning accelerator per node?
I can, the way it's been done so far is there are accelerators associated with servers. So both GPUs and TPUs have been done that way. NVIDIA just recently announced this, the Hopper GPU is not available yet, and there's going to be this Grace version that goes with it that has a 1 GPU and 1 TPU put together. In the past, TPUs and GPUs have been connected on trays over PCIe buses. So the fact that it might be closer might be interesting. That might be interesting if they weren't, isolated address spaces and separate memories. That might be more efficient. I think that's an interesting thing to look about. Whether it be further disaggregated, I've been concentrating on training. I don't know how important that's going to be. The training workloads are kind of predictable. I mean, they run for weeks, and data access and stuff. So what's interesting for me is the deep neural networks is pretty pliable. If we were using spec benchmarks or something like that, you can't change the line of code, but they're willing to modify their models because they aren't that big to adapt it to your hardware. So the arguments for disaggregation that probably make sense for some workloads like databases and stuff like that, I don't know how important that's going to be, but I think it's certainly interesting to have the CPU closer in the same address space. Okay.
Okay, thanks. A quick related question by David Grant, related to the earlier question about using machine learning for PUE improvement. The question reads, is machine learning for improving PUE even worth pursuing if the PUE is already less than 1.06?
Yeah, I think that's an interesting question. I mean, you might be able to save, there might be money if you could save money easily, companies would like it, but yeah, there's not a lot of headroom left there. And this question about, I saw the comment about it's not specific to ML. Yeah, it is though. I think I would disagree with that. Given you're a machine learning person and you're going to train somewhere, it's up to you where you train. The easiest thing to do in the cloud is to pick, you can train anywhere. So pick the green location. If you don't pick a green location, your carbon emissions will be much worse. And the point of the 4Ms is there's a bunch of things you can do relatively easily that will dramatically reduce carbon emissions. So yeah, it's absolutely something you can choose to do or not to do, and which have big consequences. Go ahead.
Thanks. Yep, thanks for addressing that. The next question is, do you have any thoughts about neuromorphic hardware to improve energy efficiency?
Just a little bit. Kind of in general in computing, you'll hear of new ideas, and it's hard to evaluate. So like when Kenneth and I do our textbook, what we say, there's all these papers. How do we decide which ones to include? Well, we include the ones that companies put in products and themselves, because it's hard to tell how feasible a new idea is, but if a company's willing to bet, make the investment in it and put it in the marketplace, then that's interesting, and we can evaluate it because we can run benchmarks on that commercial hardware. So for machine learning didn't used to have benchmarks, but I think 4 or 5 years ago, I helped with other people to do the ML perf benchmark, so that there are now standard benchmarks that people can run. So a lot of excitement has been around neuromorphic hardware about its potential, which has a very different model. But the question will be, well, then, if it's a really interesting model, can you run the benchmarks, right? Well, people, and how well do you do? And that's the test there. And so just like with all these venture startups, all kinds of ideas, a bunch of those ideas that were tried by these startup companies, those companies aren't around anymore. Many of them never published MLPerf benchmarks, I presume because the numbers weren't very good. But this is kind of what we do in computer architecture: spend millions of dollars or billions of dollars and put it in the marketplace and run benchmarks and see which ideas win. So I think the challenge will be for neuromorphic computing to start putting some results out there on these standard benchmarks and see how you do. And if you can match the quality scores and you can do it more efficiently, I can easily imagine that the field would shift. But in absent of that kind of information, it's unlikely.
Thank you. In alignment with really the general interest in this community, again, another question along those lines about operational uses of machine learning for improving efficiency. Examples like smarter scheduling according to seasonal or daily variations in PUE. Any thoughts or comments on that? Mm-hmm. Yeah.
Because renewable energy is not constant day and night. That's a thing that people are working on, is doing energy storage. There has been work at Google to try and schedule jobs in times when there's more renewable energy available, like more than people can use, to try and use at those times. Also, what isn't, which is not explicit in our data, is how well utilizes the hardware. Because unfortunately, when hardware is idle, it's still using energy. It doesn't really go to zero, right? So if your machines are underutilized, then that can be inefficient, energy inefficient. So scheduling would be a way to improve the kind of the average efficiency of these data centers by getting more work done rather than having machines idle. So that would be another good use of machine learning, using machine learning to improve energy. Yeah, so there's kind of two things that are going on in this exciting field. There's kind of hardware or systems to make ML go faster, and then there's ML to make systems go faster, right? And I didn't talk about that second one, but I think it's a really interesting area, and I think it certainly applies in general. If you make things go faster, it's probably more energy efficient. But you could specifically focus on utilization and other factors to try and improve the energy. Yeah, we use liquid cooling in since the TPU v3. That's been using liquid cooling. That's more efficient than air cooling, and so TPUs switched over with third generation, and things are getting bigger and hotter, so it keeps being liquid cooled.
Great. Thanks for addressing that. A few more questions popping in. So just some comment there about efficiency benefits of about 85% utilization versus 95. I believe that related to the earlier question. And then does the 4th M location really change things in terms of overall carbon footprint unless a less favorable location is actually shut down or migrated from?
Yeah, there's a kind of bunch of questions about this. Kind of what's different about the cloud is, first of all, it's growing. I know it's different, but the cloud is growing. So if we send more jobs to locations, geographic locations that are energy efficient, future data centers will be built there. So if there's a man, and one of the really nice things about this, the work we've been doing is in the last year is Google customers or potential Google customers are starting to think about these things. And so I'm starting to get indirect conversations like, well, what would happen if I run this job in Oklahoma, which is very windy and has very high % carbon-free energy? What would be my carbon emissions? So customers are starting to care about that. So if people want more computing in Oklahoma, Google's going to build more data centers in Oklahoma. So there's kind of this future side of it. Also, data centers are unoccupied a lot of the time, and renewable energy is underutilized a lot of the time. So there's actually a fair amount of headroom. So if we drive more of the workload from the less energy clean areas to the cleaner areas, there is a lot of capacity, right now to get more work done there. So yeah, it's not a zero-sum game where everything's at the brim, and if you do some work at this one, it's got to spill over to the other. It's not quite that simple, both currently and in the future. So there really does make a difference there. And if we start, if Google's in 3rd place in the US in the cloud, and so if it starts getting more market share because it is using cleaner data centers, that's going to encourage Microsoft and Amazon to react, and we'll get this kind of virtuous circle where people would start competing on having cleaner and cleaner energy. Google has announced as a corporate goal that by 2030, 100% of its energy will be renewable. So it's put a flag on the target, and it's hit its goals in the past. It's very aggressive, but they believe that between the increasing amount of carbon-free energy and investments in carbon, in storage techniques to store carbon-free energy, that they can get there by the end of this decade. And if it turns out to be a commercial advantage as well as being good corporate citizens, then that'll encourage others to follow.
Thank you. And I guess the one final question for this slot is, what is your, or perhaps Google's perspective on recovering wasted heat? And if we have a number there in gigawatts.
Yeah, I'm not an expert in that, but that's absolutely one of the things. There's all kinds of innovations in the data center to try and make them more greener, more energy efficient. I don't know specifically on that one, but they're in general in the data centers, there's putting them in much cooler locations and using ambient air and things like that. So I wouldn't be surprised if people have looked at whether there'd be some heat recovery gains in that area, but I don't know about that.
Okay, and with that, let us cap off this round. And thank you so very much, Dr. Patterson.
All right, stick around for John. Stick around for John talk. He's a friend and a really good speaker. So.
Yep. Indeed. Thanks again, Dr. Patterson.
Okay.
Yep. And I'll take over the screen share here.
Yep.
And with that, next talk, again, an exciting talk by John Schalf. The talk title is Heterogeneous Integration Roadmap for the Future of Energy Efficient HPC. So for folks on the call, John Schalf is the department head for computer science, Lawrence Berkeley National Lab. and recently was Deputy Director of Hardware Technology for the DOE Exascale Computing Project. Dr. Chalk is a co-author of over 80 publications in the field of parallel computing software and HPC technology, including 3 best papers and widely cited report on the landscape of parallel computing research, A View from Berkeley, which he did with Dr. Patterson there. And he also co-authored the 2008 Exascale software study, Software Challenges in Extreme Scale Systems, which set the DARPA's information technology research investment strategy. And prior to coming to Berkeley, John worked at the National Center for Supercomputing Applications and the Max Planck Institute for Gravitation Physics, or Albert Einstein Institute, where he was co-creator of the Cactus Computational Toolkit. With that, thanks again, John, for participating as always, and over to you.
All right, thank you. All right, let's see here. Try to share this. All right.
Yep.
Does that come through?
Yes, it does.
All right, let me move chat over to here. All right. Okay, so Dave already covered this, so I don't need to spend too long, but this is from the Semiconductor Research Corporation's decadal plan. This isn't the energy growth rate of ML alone. This is basically all of the microelectronics industry. But the projection is that at current growth rates, it's going to be 25% of primary energy by 2040. And if that would be if we had projected tapering of Moore's law. If we still had Moore's law, it would moderate that projection some. But in order to meet our climate goals, we have to go to a regime of ultra energy efficiency, where the rate of improvement would actually have to be greater than what Moore's law has historically delivered to us for the past 50 years. And that's simply because of the demand for compute cycles, both the IoT and the hyperscale data centers put together. And so the trend that, now that we don't have the wind of transistor shrinking in our sails, we're moving towards an era of diverse acceleration, starting with the GPUs, but we're seeing an explosion of other kinds of accelerators. You have the wafer scale stuff like Cerebrus. We have data flow is coming back into vogue again, a number of different data flow type accelerators. And if you really want to incorporate, the overall trend is trying to co-integrate these kinds of accelerators together in diverse, extreme heterogeneous systems in the future. And this isn't really kind of like a computer architect's pipe dream. This is actually the way things work in nature as well. So if you think of, in the good old days before Dennard scaling fell off, we had powerful general purpose processors like the Xeon and the Power. But then you have post-Dennard scaling scarcity. You end up with many lighter weight cores. So here we have a couple of dozen really aggressive Sparrows. And so that's Knight's Landing or the AMD or Cavium Marvell, and even GPUs to a certain extent are moving towards many of the same cores, but lighter weight. So that's how nature responds. That's how computer architects responded. But if you continue to have food scarcity, especially post-war scarcity, then the critters have to go after different food. And so in this case, we have Amazon, Apple with its many different kinds of accelerators that it employs in an iPhone chip, Google with a TPU, Amazon with a Graviton 2, and other kinds of accelerators appearing in the market. Now you see this differentiation, the Darwin's birds here with their specialized beaks. So this is a natural progression to go that way. And the challenge with moving towards architecture specialization is how do you co-integrate those specializations together? And so the heterogeneous integration roadmap is run by the IEEE Packaging Society and many industry leaders working in IEEE to provide a roadmap, not just, if you read the report, it's huge, it's 600 pages, but it covers both the market targets for this kind of advanced packaging for co-integrated specializations, but it also covers the roadmap for the technologies that will enable this kind of advanced packaging. And that's really exciting because it shows a path forward for 5 consecutive generations of doubling, performance doubling, not based on shrinking transistors, but based on co-integration of specialization. And the reason why you need to focus on this kind of advanced packaging and co-integration is that with the current way that we package things with SerDes, you have a lot of drive current, and the power going to your off-chip I/O is matching the power consumed by the flops that are on board the chip. And Dave mentioned that earlier. So this is another view from Gordon Keeler and also from SRC, showing that the actual data movement power consumption is one of the leaders in this. And so we really have to go to advanced packaging technology to go after that. And one of the approaches is of this kind of co-integration of specialization is chiplets. A chiplet is a very specific packaging. I'll point out that there's lots of different kinds of advanced packaging. There's MCMs, there's 2.5D, there's 3D integration. The chiplet is a form of a 2.5D integration, and the way it achieves performance is through much tighter bump pitch, I guess, basically for the signals. So rather than growing your SerDes to absurd 120 gigabits per second for SerDes, because there's a limited number of pins in a package. The growth rate for pins is like 1.5% compounded rate of growth. And so to make up for that, they had to increase the SerDes to really high data rates. This going to 2.5D integration with these solder microbumps or copper micropillars enables you to go back to more regular SerDes rates, like 4 gigabits per second or less per pin, and you can increase the pin density by a factor of 100 or more. This gives you also the opportunity to co-integrate many different kinds of specialized functions inside of the package without paying the high power cost of moving data between those components. So as I said, it's one of many advanced packaging technologies, but it's one that's very interesting for other properties. So one of the challenges moving forward, though, with co-integrated specialization is that it isn't decreasing the cost of our physical design of a chip. The design and verification of chips are still very expensive. So you want to be able to reuse that IP after you verified it and designed it. So, the way that the current licensable IP market has really taken off is through reuse of IP. So we went from 2002, where there was only 10% IP reuse, to today, where once you've designed that IP block and verified it, now you can reuse it for many other applications. And we're seeing 90% reuse of licensed IP blocks. The next step, of course, is to take reusable IP and package it into these chiplets. So now the vision here is that you can have reusable function blocks that are specialized for different purposes, but you can reuse them in many different packages. And you just grab your chiplets out of the different drawers, your commercial IP for memory, SerDes, and processors, your reusable function blocks for specialized acceleration, and also your big data movement. And the government, from my perspective in HPC, the government's interested in having its own specialized chiplets in those drawers too, that they can mix and match with commercially supported IP. This is also something that is observed by the mega hyperscale data centers. This is on the left here is from the Meta, Facebook. at the Open Domain Specific Architecture Workshop. So ODSA, Open Domain Specific Architectures, is an offshoot of the Open Compute Project, which is basically trying to create a marketplace for components for the hyperscale data centers like Meta and Microsoft and Google. And they do so through open standards for the components that they need. This new sub-project, ODSA, is focused on domain specialization through the chiplet technology and this advanced packaging. And so they're seeing, we're moving from an era of standard, everybody's a general purpose CPU, programmable CPU technology towards increased branching and specialization for many different submarkets. And again, this goes back to and a colleague of ours, Neil Thompson from MIT CSAIL, is pointing out that as Moore's law is tapering off or as fab prices go up, we're moving from a transistor focus where you'd scale down your transistors, you get better performance cost, and you get market growth, which would in turn drive this virtuous cycle. We're moving very rapidly towards a systems focus. And in a systems focus where the transistor scaling isn't driving things anymore, it's really about system performance and co-integrating the right kinds of specializations with lower cost but increased functionality, and the new virtuous cycle is going to be driven by this kind of advanced packaging. Oops. So let's see here. And so, this is the ODSA vision, is creating this open chiplet marketplace for hyperscale data centers. And so they're focusing on open die-to-die interfaces. There's another related activity called UCI Express, which is creating a die-to-die interface standard for CXL. But the ODSA is focusing on the ARM-based die-to-die interface like AXI or AMBA, and also PCIe. They're creating reference designs that show the complete demonstrate what the electricals would need to be for those open die-to-die interface, and then reference workflows, which are open practices with your foundry. How do you get from end to end, from a concept for a chiplet to a standardized and qualified part that can be put into these standard packages? And this is a very compelling vision also for HPC, for being able to do IP reuse for high performance computing, because we can't really afford to be spinning our entire chips from scratch. And so, we're in discussions with them to work together with the hyperscale data centers to bring this kind of open chiplets marketplace into being, which is exciting. And this is the last thing, the heterogeneous integration roadmap worked out basically with technology that we know exists today. And this is in the heterogeneous roadmap document, 5 generations of not increasing the density of flops, but actually increasing bandwidth density. So ISO power, 5 generations of doubling of bandwidth density is achievable with the technology we know and have demonstrated in the lab today, and possibly could extend this roadmap out and so further. And so that's really I guess exciting. With Moore's law tapering off, there's another thing that we can grow, and we can improve the energy efficiency of bandwidth delivery for future systems. All right, so now I'm going to hustle through this last thing here, since I'm in my last, I guess, five minutes in my slot here, but I wanted to talk briefly about resource disaggregation, and this touches on some of the things that Dave was talking about earlier. In the modern data center, both for HPC, but also for the hyperscales, we have diverse node configurations for diverse data center workloads. For example, in training, you have these DGX type nodes from NVIDIA, where they're tightly connecting these GPUs together. And this is in order to exchange the gradients for the weights, so you can accelerate training operations by having each of these GPUs handling a different subset of mini batches, but then normalizing the weights across them. But if you go to inference, there's no point in having the GPUs cross-connected in this way. In those high power connections, the data movement's very expensive. You really want to connect all of your data channels to the outside world in order to stream data through and do inference on it. For databases, you might want to connect directly to a ton of non-volatile storage. For graph analytics, you probably want to actually bring a lot of the graph into your high bandwidth memories and also have a lot of connectivity within the data center. And this constitutes 4 different clusters, and there's actually more workload configurations than this. And if you run out of one of these configurations, then you're hosed, or if you underutilize the configuration, you have a lot of idle hardware on your floor. And modern data centers are at about a 30% utilization rate. Another more specific example is memory underutilization. There are jobs in the workload at, for example, the NERSC HPC center that require more than 75% of the available memory per node. That's about 15% of the workload, but over 75% of the workload use less than a quarter of the memory. And all that memory is just sitting there idle. It consumed capital cost when you bought it and it's sitting there idle. And it's also consuming power while it's sitting there idle in the system. So this is a huge amount of waste. This is called maroon resources in the data center speak. And so this isn't a new thing. This is actually a diagram from Intel, I believe, originally, that right now the state of the art is you cram everything that you need into each of your pizza box servers and you replicate and repeat to build up a supercomputer or a data center. But in disaggregation, we try to pool those resources and then compose them into customized nodes that we need to serve those diverse workloads. The current solutions that they use to implement these in production in Meta and at other data centers today use PCIe or 100 gigabit Ethernet in order to implement disaggregation. So this is already happening today. This is significantly inferior to RAM bandwidth, and as we know in HPC, we're huge consumers of bandwidth, and so this isn't an acceptable solution for an HPC context. So this is where the photonics stuff comes in. And it's an interesting confluence of a lot of technologies here that make co-packaged optics and photonics a really exciting solution, and that's only been available recently due to a number of advances. The first, of course, is this advanced packaging technology that I was talking about earlier, where you get the solder micro bumps. You get your bandwidth by operating wide and slow. So many more connectors than you could if it was just pins, but at 10 gigabits per second or that range. The second is the dense wave division multiplexing from Silicon Photonics. They've been promising this for a long time, but this confluence of the advanced packaging that operate at a slow rate per channel with a lot of channels actually aligns very well with where dense wave division multiplexing, where each of these rings encodes a separate frequency of light at a lower data rate, but all of them can share the same optical fiber. So you can get terabits per second out of each fiber. And the last thing, and this is most recent, is the emergence of comb laser sources. If I had to have a separate laser, carefully hand-assembled indium phosphide laser for each frequency of light, that would be unaffordable in terms of packaging cost. So these comb laser sources generate hundreds of frequencies of light simultaneously from a single laser package. And you bring this all together, and now we can go wide and slow at terabits per second, 8 fibers, you get terabytes per second. Now we can escape a high bandwidth memory from the package. And so instead of having, this is our current state-of-the-art GPU, you get your high bandwidth memories, but it's prime real estate. There's a limited number of those memories that you can array around a GPU. So we end up having a lot less memory capacity that we really want or really need, especially for these huge transformer type networks. Instead, if we use that space and you put the photonic co-packaged, SIP, now you can escape the package at terabytes per second of bandwidth. And if you can go now anywhere in the system, now you can actually have an optical circuit switch like Mingwu's and Berkeley campus, and you can connect up what you need. If you don't need much memory, then you don't connect it up. If you do need more memory capacity, you can cobble together as much memory as you need, depending on the needs of your workload. And in this manner, we can, with these terabyte per second link technologies, we can take the same set of resources, configure for training or configure for inference, and do so in an energy efficient manner and eliminate. So you can basically operate the same system without any loss of, with minimal loss of throughput, but now we don't waste 75% of the resources in the system because we can custom configure them as needed. So I'm going to stop there and take questions.
Thank you so much, John. Folks on the call, please use the Zoom chat for questions. Okay, question number one. EIA data shows that the US annual electricity growth rate remains below 1% across much of the projection period in the reference case. From the March 2022 report. Note that the projection period is 2021 to 2050.
There's concern that that's actually an anomaly due to and right now we're seeing these supply chain things, especially in the energy market, because suddenly the economy is roaring back to life. So there's a lot of speculation about what that means in the 2021 period, as you know, with COVID.
Right.
So I don't know the answer to that, but we're going to have to wait and see to find out which is true.
Okay, thank you. Any other questions on the line?
I'll make one other comment here with, this is from Dan Reed. You should read this article, it's really good. We had been focusing on our technology suppliers being the usual big five traditional computing. But you know, Dan's pointing out that actually control of the computing ecosystem is from these trillion-dollar US technology companies that aren't the traditional chip suppliers. So this is another reason why we're really interested in working together with the ODSA and the OCP and the hyperscale data centers to figure out how to have configurable specialization for HPC, because they are crafting the market that will supply them. And we need to learn from them how to make use of that market in order to achieve energy efficient HPC in the future. Because it's always going to be this Branscombe pyramid here.
Yeah, this is interesting. A question from Natalie. How do you figure in the cost of equipment no longer being used?
How do we figure, Natalie, can you elaborate? I'm not sure how you mean no longer used.
Yeah, I mean, you're talking about utilization, which is a really important concept, trap capacity, or
Yeah.
you know, whatever you want to call it. And that, I think that is extremely important. But now I'm thinking like what Matthias asked or what Jim was asking about, you know, data centers that already exist or equipment that already exists. I mean, we do have a really high refresh rate. And I love your idea, but you know, one of the other things that we do need to consider is we're just constantly replacing stuff and throwing stuff away. You know, there's a big energy cost there and a big carbon cost too. So I'm just wondering if you have any thoughts on that.
Well, you know, with the performance of so let me take a step back, you know, with the chiplet stuff. So right now, when you want to respin a chip, if you want to change an IP block on a chip or like put a better SerDes on your chip, then you have to respin the entire chip. Something that the Xilinx and the FPGA people figured out a while ago actually is that you know, you don't have to be at the most recent technology node to get a good quality SerDes. And the same is true for a lot of other things like memory controllers and things like that. So the notion here is that, well, why make node? Why not spin things at the technology node where it's most efficient and stop when shrinking the size of the transistors no longer benefits the that component? So you could, for example, have a drawer full of memory controllers that are built in 14 nanometer technology. And even as other components that benefit from shrinking the transistor march forward, you can keep pulling things, reusing stuff from that same older technology node, which is less energy intensive, more cost effective, and co-integrate them together. So in a sense, it's reducing that kind of waste that you're describing because you're throwing out everything each time you do a technology refresh with a current monolithic design strategy.
Thank you. And then, of course, a question on the role of software in improving energy efficiency of HPC. If you'd like to comment a bit on that, the context of this
software. Stuff. Yeah, so there's, if you go to Neil Thompson's website too, he actually did a multi-decadal survey to attempt to measure the extent to which algorithms and software are implicated in improving energy efficiency. And it's really interesting because in some areas, the software hasn't seen any improvement in a decade or more. Other areas, there's multiple orders of magnitude benefit, but they come in fits and starts. So it's kind of not a smooth growth path like we expect from Moore's law, but in fact, a more kind of fits and starts when somebody comes up with a new algorithm and then people optimize the hell out of it. You get a huge gain in a short period of time, but you never know when it's going to happen. So it's crucial, but it's also kind of unpredictable, but it's a great article. So neilT.com, you should check it out.
That's a good reference. Thank you. There was a comment there from Matthias that well, silicon photonics reconfiguration is currently not in the scope of data centers or cloud providers. So in terms of software, I guess schedulers and operating systems of data centers have to evolve to support this.
Correct.
So any comments on that?
Absolutely. I mean, this notion of resource disaggregation with silicon photonics is fairly new. I won't say that it's completely not there yet because deployed in cloud data centers today are PCIe and CXL based disaggregated systems. So as I mentioned earlier, the bandwidths aren't anywhere near the kind of high bandwidth memory type bandwidths that we can deliver with silicon photonics. So silicon photonics is going to be a huge boost to those solutions. But I wouldn't say that it's completely zero in terms of schedulers and existing data centers. There are companies like Fungible. I know that Google, I've heard them talk about their own internal solutions, and Facebook has been doing this for a number of years using, active optical cable type technology. So it's non-zero, but there is a huge amount of research in improving that because security is a big concern. And improving schedulers is a big concern, but it's not true that we're starting from zero here. There's already commercial solutions in the disaggregation space that are deployed.
Thanks. And to that point, it's really the entire ecosystem from gates to wide area network connectivity. All of those would need an upgrade, right?
Yep, that's right.
Another question. Yeah, sorry, go ahead. Yeah.
Yeah, go ahead.
How would quantum computing impact energy consumption? Any thoughts there?
Well, I mean, right now, because of the limited number of qubits we can actually keep coherent, it limits the size of your quantum data center. But I think it's important to understand that quantum computing is great. It's expanding computing into an area where digital computing isn't that great. can solve, combinatorial optimization problems that would take years to solve on a conventional computer. But and so it's great that we develop it, but it isn't a replacement technology for what we do with our current HPC and data centers. I like to use the analogy of, so I've got Microsoft Excel, I use it to balance my checkbook. If I have a quantum Excel, then it'll be the superposition of all possible balanced checkbooks. So it's solving a different problem. And if it was a neuromorphic Excel, it'll say it looks balanced to me. And if you ask it again, it'll say it looks balanced with a 80% confidence interval. But these different models of computation are great, and but they aren't replacement technologies. They aren't directly competing with each other, I guess is the point. They're expanding computing into new directions where digital isn't the best technology.
That's a great example. And with that, I'd like to cap the session off. Thank you so very much, John. Folks on the call, we have a quick 5-minute break, and then we will move on to the next a discussion panel on sustainability, to be driven by Jim Rogers and participants Steve Hammond, Johnny Dickus, and Mark Monroe. 5 minutes for a quick break, and see you guys in a bit. And I'll urge once again the non-speakers on the call to please mute your microphones and turn off your webcams, just in the interest of saving bandwidth.
So Sid, do we want, well, Steve's here. Do we want Steve to go ahead and get his slides prepped so that we can move quickly through the
Yes, please.
Through the intro slides?
Yep, sounds good. Yes, thanks, Jim. Steve, would you like to do a quick
another
share?
point of order? Right. So, do you want me to introduce each of them? I have that
Yes.
information.
Yes, please, Jim.
Okay, I'm happy to do that.
Thank you. Steve, would you like to do a quick slide share check? Okay, you're coming through. Great, thanks.
Very good. Do we want to do the same thing for Mark and JD?
Yeah.
Just to do a quick slide, just to make sure there are no technical problems.
And
JD,
I don't have any slides, so I'll just talk for a brief intro.
Okay. Awesome. Okay, and then Mark.
Yeah.
I'm sorry. I'm sorry, JD.
Hi, how you doing, Jim?
Good. How are
Mark,
you?
Steve?
Do you want to do a quick screen share of any slides that you want to show?
I don't have any slides that I want to show.
Okay. Okay. All right. All right. So
Great.
Steve's
Thank
got
you.
a couple. We'll do that. I'll basically introduce the three of you, and then and then basically go straight to opening remarks. And then Sid, we are a little bit over. We're about 15 minutes over. So how much do you want to still take a full 50 for the panel?
It still works. We are still 50 minutes would work. Thanks.
Okay.
The picture is decidedly shaggier than I am today, huh?
Yeah. That's your COVID picture, right?
I think I labeled it winter coat. Shedding is already happening.
You should have seen my pre-COVID stuff. So,
Okay, let's wait for 2 more minutes and we should get started.
Okay. And then Sid, I would assume that your expectation is that just the four of us will turn on video after Steve's PowerPoint.
Yes, please, if you so choose. Others on the call, I please request others to please turn off their webcams. Thank you. Thirty more seconds and we can get started.
Looks like a nice day in your background, Steve, down in Golden.
At least when the picture was taken.
That's right. Looks very similar today so far, but aren't they predicting snow for us for Friday?
I think
in the mountains.
Yes. No, I think snow's in the forecast here Saturday overnight.
Yeah. Gotta love Colorado.
Okay.
It just allows him to it just allows him to brag about his PUE a little bit more. So
yeah, but he's running that inside of the data center at like 40 degrees Fahrenheit. So
over to you, Jim, whenever you're ready.
all right, Sid, are we ready to go? All right. So Sid, thank you. So we're going to go ahead and move on to a discussion panel on sustainability. And I'm delighted to say that we've got three representatives from very different perspectives. Mark Monroe is here from Microsoft, right? So we have an industry perspective. We also have Steve Hammond from NREL. So we pick up basically one of the federal data centers from a very high performance computing and efficiency perspective. And then John Dykus. So JD is here representing, basically, he gives us a federal viewpoint. So I think we've got three good viewpoints to look at sustainability. Steve's got a couple of slides. So Steve Hammond is the Senior Research Advisor in the Mechanical and Thermal Engineering Sciences Directorate at NREL. And he leads efforts to address industry decarbonization and challenges in the optimization of integrated complex systems, including smart urban systems, low carbon integrated mobility, and catalyzing a clean energy transition. And as many people know, he was the founding director of NREL's Computing Science Center. So Steve, why don't you go ahead? I know you have a couple of slides to start us off. And while you're getting that ready, what I thought I might do with this panel is we'll let Steve do that. And then what I'd like to do is give each of you just kind of an opening series of remarks. So what should we, right, there's 100 people on this session. So what do we take away from this panel, right? So what should we focus on as the participants, right? Are we looking at energy cleanliness or renewable energy, carbon reduction, environmental impact, right? We all have a little bit different perspectives. So if the three of you could kind of help us understand what do you want us to take away from that, I think that would be great. All right, so with that, Steve, why don't you go ahead?
Yeah, thanks, Jim. Steve Hammond from NREL. Many of you who have visited the campus have had the opportunity to visit the Energy System Integration Facility. There's office space up front, and then there's a data center in the middle, and then high bay laboratories in the back. We took special care to integrate the data center into the facility and into the broader campus, take advantage of opportunities for waste heat capture and reuse as part of our focus on sustainability. Get rid of this. So part of what we've done within the mission of at NREL is focus on holistic approaches to push the leading edge of data center sustainability. Some of the areas we focused on is our carbon footprint, considering embedded greenhouse gas emissions in electricity, backup generators, our electrical supply. We focused on extreme efficiency in terms of the liquid cooling, so water use. So depending on where you are, availability of water can be an issue, but also the water treatment is embedded carbon because it takes electricity to actually treat the water and distribute it. As I said, liquid cooling is really important. So component level liquid cooling, we've been doing that for over a decade now. And with that, focused on the waste heat capture and reuse. So we took a chips to bricks focus, thinking about, getting the heat exchange closest to the chips, and then not being satisfied once the heat was out of the back of the racks, but thinking about what we do with it from there. So from a data center efficiency perspective, I think one approach to how you think about your enterprise is inventory your facility. Think, be honest, about the puts and takes. What are you bringing into the data center, not just to your racks, but to the facility? Do you need diesel for running backup generators? What's the carbon intensity of the electricity, depending on what region of the country or world you're in? That can vary widely. And then your water usage. And then what are the outputs? What do you do with your waste heat? Do you simply eject it? Are there opportunities to reuse it if you have a data center sort of off in some remote place just to take advantage of cheap electrons? There may be minimal opportunity to reuse that waste heat. But if you're talking about tens to hundreds of megawatts, it just seems criminal that we're just ejecting the waste heat, that we're focusing on the bytes and ignoring the BTUs. And then what do you do with decommissioned equipment? This came up before. How do you, think about a car. Most of your car, when you're done with it, gets recycled. The scrap metal gets reused. Any precious metals are also reused. So can we do the same thing? Can we think about the holistic, sort of cradle to grave of data center in the computing enterprise? And I sort of pose this as a question. Some folks pay careful attention to purchasing renewable energy credits, but is that kind of like paying someone else to want a diet for you? Some of the things we've done in our data center was focused on water reduction. We worked closely with Johnson Controls and Sandia National Lab on a collaboration, installed a prototype dry cooler, the thermosiphon system. What we were able to demonstrate there as taking an industry prototype and work with industry and help Johnson Controls bring their Blue Stream product to market was that we could reduce our water consumption, which is about 2 million gallons a megawatt year. We could cut that in half, and we preserved the extreme efficiency, which Jim mentions is about, our PUE is about 1.026, 1.028, something in that, depending on the time of day, but below 1.03 on an annualized average. We've also looked at hydrogen fuel cells in the data center, both in terms of primary and backup power role. So we have a hydrogen storage yard in the back. We have on-site generated green hydrogen. So in a primary role, you could make short runs of DC power from a fuel cell. You'll see in the picture here, it's a automotive fuel cell from Daimler. They provided to us for a year. So you could think about row level integration of short runs of DC within your data center rather than distributing AC and then the conversions. You could also consider that as a backup power to replace your diesel generator. They're responsive. You can almost eliminate your battery backup because within about a second they go from cold start to fully handling the load. And then another consideration is if you've got hydrogen, because there's silent and zero emissions, you could use them for load shedding and reduce peak demand charges. So my guess is that if maybe in a decade when hydrogen is as available as natural gas, that data centers might look a lot differently than they do now. And I think with that, I'll wrap up. Turn it over to Mark.
Thank you, Steve. Yeah, so JD, John Dicus, he is the Department Program Manager for IT Sustainability and Data Center Optimization. He has an IT background, including systems admin, systems engineering, facilities management, operational cybersecurity. He's he is certified as a data center energy practitioner with a BS in aeronautics from Embry-Riddle and AS degrees in computer science and armament. I appreciate JD joining us today because he's going to give us kind of a Fed policy perspective that maybe we don't quite see. So JD,
appreciate it. Thanks a lot.
Yeah.
Thanks, Roger, and everyone. Right. Yeah, it's really kind of hard. We're sitting up here at headquarters, and under the Data Center Optimization Initiative, we're trying to optimize all of our data centers across the agency. And so looking at that legislation and trying to turn that into something that's really feasible and workable and where the rubber meets the road, right? And working with the national labs there, just as you just saw, all these different technologies. One of the things I didn't hear Steve mention, maybe I missed it, was like to hear the rear door heat exchangers. You talked about the thermal siphoning technology, the fuel cells, right? But how do we work together, right, from a federal standpoint with that legislation, there's different things like the Energy Act of 2020 and so forth, and try to turn that into real things like we've been talking about today. And we heard, Google talk about, PUE at 1.04, and we just heard Steve with, he's down at 1.26, 1.28, and so forth, 0.28. So, what are the types of technologies that we can use and get in place to try to meet those mandates of getting to zero carbon emissions, or carbon neutral, right? And so all these things today that we've been talking about, I think are very interesting and enlightening from a federal standpoint, to see the industry and the federal government working together to try to tackle these challenges that we face moving forward. So I'm sitting here today, don't have the PhD in supercomputing and so forth, but from a policy perspective and trying to drive these objectives and mandates that we get down from legislation, how do we get there in 2030 and 2050 with the zero emissions? And so I appreciate all the thought that's been given today, and I look forward to listening to more and learning more as we try to tackle these challenges, and appreciate everyone's time today and all the efforts that have been put forward. So thank you. I'll turn it back over to Roger.
Okay. Thank you, JD. So the third panelist is Mark Monroe. He is a principal engineer in Microsoft's Data Center Advanced Development Group, working on future systems for energy, water conservation, and automation. He is a Six Sigma Master Black Belt with a focus on change acceleration in corporate settings. And he's led several industry consortiums, including iMasons and the Green Grid. And he's served on the board of directors for the Center for Resource Conservation in Boulder. Mark, you ready to give us some opening remarks, and then we'll start with a couple of fun questions.
Sure, sounds good. So just I wanted to go back to Microsoft's commitments and sustainability report. Some of the things that Microsoft has committed to, I feel really good about as a sustainability person. More than a year ago, Microsoft committed to be carbon negative, not carbon neutral, but carbon negative by 2030, and by 2050 to remove all the carbon from the atmosphere that the company has ever generated. We've also talked about being water positive by 2030. That means in the communities where we are, we'll generate more clean water, more potable water than we will consume as a hyperscale compute company. We've got initiatives around environments around our data centers, around e-waste and all waste, getting to zero waste at all the data centers, and we're making progress. And I'll just put a URL in the chat window. that you can jump to see the latest sustainability report and talk about progress that we've made towards these goals. I'm really proud of the company for kind of stretching beyond just zero and going for the negative commitments that we've made. And obviously the way that we do that as a huge energy consumer is through the tools of offset and inspiring net new energy on the grid. I liked Steve's comment about paying someone else to diet for you, but the way I think of it, Steve, is more like we bought a truck full of Evian and put it into the town reservoir, so everyone gets a few molecules of Evian water. And we get the credit for putting all the Evian in. So I do think it's important that the data center companies and the hyperscale companies are focusing on a couple of things. The 100-100-0 program that Microsoft has, or the 7x24 renewable that Google has, are where we're not only looking at offsetting the annual energy that we use, but offsetting every single hour with an hour of renewable production, and hopefully on the grids where we are consuming it as well. So again, that tank truck of Evian looks better and better because we're getting it closer and closer to the resource that we're actually using. And others benefit from the renewable electrons that are on there as well. There's a number of things that we could talk about. I think that we'll get to some interesting topics on the chat and on the questions that come up. So I'll end there for now, and happy to answer any questions if people have.
Yeah, but hey, can I pull that thread just a little bit, right? So this was a really interesting one to me. Because Microsoft is, you're a corporation, right? And you're enormous, and you use an enormous amount of power, but you have external stakeholders and shareholders and consumers. You have all of these other people who are pushing in so many different directions. They're pushing on business objectives, on profit, on stock price. And then you have all of these social, economic, other indicators. How do you balance those? Right. It's really fascinating to me. So how do y'all balance that, right? Because these things cost a lot of money, but you also have to drive shareholder value, but you also are getting beat up on Twitter.
So I actually don't think so, Jim. At least from my experience, we didn't, it cost us less to be more efficient. We just, it's expensive to do a retrofit. Yeah. But it doesn't have to cost a lot more to be efficient.
That's right. I would agree 100%. Is that fortunately a lot of the sustainability initiatives that we take as a company and as an advanced researcher in our group are also economic benefits as well. And we do have a responsibility to all those stakeholders to make profits, to improve the value of the company. But I don't see how you can do that these days without considering your carbon footprint, your water loads, your e-waste, your contributions to the community. We start to talk about being a producer consumer. Obviously, consumer is huge, but what else can we do for the community that where we have data centers located, that we're not just a consumer, but this kind of prosumer that makes us welcome again. It's interesting to me that data centers in the span of about 10 years have gone from please in my backyard to not in my backyard. And we're hoping to get them back to please in my backyard, through those kind of contributions and sustainability efforts.
So I probably have a controversial comment, but that's what the panel session is for. If the electrons are green, I don't care how efficient we are, or maybe I'm a little less concerned, right? And if at least in the U.S., the current administration is saying they want to have a carbon-free grid by 2035. Let's just suppose that's going to happen. Okay, we could debate whether or not it is, but suppose it is. If the electrons are going to be green, then I'm a little less worried about improving the 1.1, the data centers with PUE of 1.1. We probably want to focus on the data centers that are 1.6 and above, right? Yeah. Although otherwise we're at point of diminishing return. But then the other things we need to worry about from the data center. If the grid is green, then we don't have to worry about, paying someone else to go on a diet for you or whatever that other debate is. We are concerned about water usage because that's still, one of the inputs. And we're also worried about recycling, right? So what do we do with the decommissioned equipment? How do we reclaim precious metals? How do we avoid, toxicity in landfills? And those are things. And then lastly, it's the waste heat. Again, if even if they're green, 100 megawatts is 100 megawatts, right? And can we reuse that? And if Microsoft wants to be back closer to neighborhoods and all, maybe having district heating or some other thing that provides a benefit, in addition to, workforce development and jobs for communities, something of those. So what my top three focusing on is water reuse, recycling of decommissioned equipment, or reclamation, managing the e-waste, and then waste heat reuse, right? So water, e-waste, and waste heat.
Yeah, so that's interesting. Because there are so many of these are almost they're too far to the right of the decimal. So let's grab the big ones like a PUE of somebody who's still at 1.67 or 8. That's pretty bad, right? There was also a really good question in the and now Herbert and a whole bunch of people have jumped in about sustainability initiatives in Europe, right? So Lumi and CSCS are doing your heat capture and reuse.
Absolutely.
And
Applaud that.
yeah, so good, but we're not seeing that really in the
well, and
in
I'll jump in. I am a huge fan of waste heat reuse, what I'll call conventional waste heat reuse, which is capturing the low grade heat out of the data center airstream and trying to find some kind of a heat consumer co-located or close enough by that, because heat doesn't travel well, right? So you got to be able to
not in air
system or get it into a consumer. But if heat reuse was compelling, there'd be more than a couple of hundred examples around the world. We did some research inside of Microsoft and tried to track all of the projects we could find, anything published about, anything we knew about, anything anybody else knew about. And we came up with about 100 to 200 sites around the world that are doing heat reuse, that conventional heat reuse. And there are tens of thousands of data centers, depending on how you count them, or even hundreds of thousands, depending on if you count the small ones. So I think we've got to come up with some different kinds of heat reuse, other than that just conventional capture, because there's a couple of problems with it. One is the co-location of the consumer, which if you look at data center companies like Microsoft or Google or Facebook or Amazon, it's hard enough for us to site a data center. And if we start adding in the requirement that we've got to be close enough to share heat with a district heating system, it gets to be almost impossible. The second thing is the seasonality of the need. I don't know what you do with your heat during the summertime, but I know you don't melt snow. Well, except here we are in May, to say that. But that's a problem. Greenhouses don't need heat in the summertime. District heating systems generally have a lower level priority than data centers for the heat reuse. So you look at projects like Odense for Facebook, and they only share heat from October to May and things like that. So,
I mean, think about the T case limits, right? They're 65, 70, right? So yeah, if you go to air is a better insulator. It's not a good conductor.
Absolutely,
of
100%.
heat. And that's what I was saying, by liquid cooling, you get 3 orders of magnitude efficiency improvement by using air, or excuse me, by using water instead of air is your working fluid for cooling.
Right.
And
you get higher temperatures as well. You get better quality heat right up in the 50 to 55 C.
A juice glass of water has the cooling capacity of a room full of air. Right. And then the pump energy to move that small amount of water is so much, another order of magnitude less. So you get 4 orders of magnitude efficiency. So physics is working at, giving you a tailwind. And if you can get, 45 degrees C, return water, there's a lot you can do with it. And higher is better. I don't know exactly where,
Yeah.
TPS limits are going, but, I've heard some rumblings of, 60 C as a return temp. There's, absorption chillers, so you can use it for chilling. So depending on where you are, globally, look for those opportunities. But, building
well,
a big
let's-
isolated
yeah. Let's go there for a minute, right? Because I think a lot of us struggle on our primary sides, even if we're doing direct-to-chip cooling with low delta Ts.
Yeah.
So the delta Ts are tough, and it's hard to effectively do any waste heat reuse because of that low delta T. And now the OEMs are telling us that the per socket is, Frontier, the per socket on a GPU is over 500 watts. And it's only getting worse, right? NVIDIA is already going, headstrong toward 1,000, but the thermal design limits are changing and the T cases are going down. So how in the heck are we going to, how do we compensate for that when all of a sudden our warm water or hot water cooling systems aren't effective? And the delta T's are still tiny.
You're back to the temperature approach that the air-cooled systems have. So there's no doubt you've got to do some heat enhancement somewhere in that heat sharing process. It's got to go through a heat pump. And fortunately, heat pumps have COPs of 4 to 6 in the range that we're talking about. So they're pretty effective movers of heat from one temperature to another. And we just have, got to build that capital cost and operating cost into the heat sharing plans that we do.
All right, great. So I want to switch
one of the
topics
things I
just a
wanted
little
to-
bit. Yeah.
Go
So
ahead.
JD, can I ask you one? I want to say, and this is for all three, are the federal timelines that we're seeing in the United States for these sustainability objectives, are these reasonable? Right? Everybody talks about 2030 and 2050 and these big targets. Do y'all think that these are reasonable? Do you think we can get there?
Right. So that's one of the things that I sit there and look at it. My mind tries to wrap around how do we drive the projects, the funding necessary to try to meet those objectives, to get those out there. Having traveled around DOE, I've been to a lot, I say all of the national labs, but I'd say the vast majority of the national labs, and I've seen where these data centers sit, right? And trying to do the heat reuse to try to get it across the campus, because the locations, let's just take Los Alamos, for example, or maybe even up here at Idaho, right? Trying to get that heat reuse to the campus to reuse it is a challenge, and it's going to take, let's just say millions of dollars to put the infrastructure in to try to get that to those locations. Other things I think about is how do we fund some of this, waste heat reuse stuff and the liquid cooling technologies that we need to look at, because as those temperatures wrap up, right, as we just talked about, getting close to 1,000 watts per socket, right? We got to look at liquid cooling technologies versus the air cooled, because that's where we're going, right?
Yep.
That's where the technology leads us. So where's the funds going to come from? Or, we're going to partner with industry to try to get that technology and get it inside of our federal data centers. But that's just some of the things I try to wrap my head around. How do we get from that legislation to actually implementing these things and get the projects, right? Because I manage a budget, and I see the life cycle to try to get something in the pipeline, right? And then get the congressional funding to get that project approved and get it online takes years. Let's just be honest. It's not like a quick turnaround. 6 months you've got your funding and you're off and running with your project. So there is some lead time necessary to get a project in place to even test the theory and to get that in motion. So that's just some of my thoughts. I don't know. It's very aggressive, 2030, especially getting the grid zero emissions by 2030. And here we're sitting at halfway we're in 22 already. So 8 years from now, I don't know. I just think personally that's very aggressive. Is it doable? I don't know.
Yeah. Well, so I looked at TVA's numbers. I looked at TVA's numbers this morning, right? And in 2005, they were at about 1,300 pounds per megawatt hour. by 2030, they're only going to be down to about 400. I mean, that's great, right? That's less than a third, but it's
Yeah.
nowhere near zero. And that's for
Right.
TVA, which serves 6 states, right? And they're still going to have a dependence on natural gas and some on coal, right? And yeah, they got tons of hydro and tons of nuclear, but they're not going to get there.
But you know, Jim and JD, we say in the internet business that internet years are like dog years. There's 7 for every regular one. So 8 years away is half an internet century. And somebody made the comment in the chat, you know, that the chips are changing super fast, and you know, Intel's got 3 going per year. So the technology is going to change a lot, and the industry is going to change a lot in that time frame as well. That's one of the difficulties we have is these different time scales, you know, where we talk to utility and they say, oh, 2050 is really close. And, you know, we're like, oh my God, that's a century and a half from now. So,
yep. Yeah. So
true.
I was talking to Steve about this, right? Because, you know, facilities have lifetimes in decades. Well, utilities have lifetimes in many, many, many decades.
Right.
And then systems measure their lifetimes in months.
And we say that our salespeople talk to customers and they get a new idea at lunch every day. So.
All right. So Sid, there are tons of comments in the chat. Are there any one that you would specifically like to call out for the panel?
I'm looking through it right now.
I mean, there's just tons of them, right? So
I agree.
I've seen a couple about desalination, and again, you know, the idea of co-location of a heat consumer with a data center is attractive from a heat reuse standpoint, but so far it's been impractical. You know, I used to, before I was with Microsoft, I used to understand how difficult it was. Now that I talk to our land acquisition team, and you know, looking for that perfect piece of land with power, network connectivity, and a greenhouse and a desalination plant. And oh, by the way, you know, Google's land acquisition folks are out there, and Baidu and Tencent and you know, all the other hyperscale companies all bidding on the same piece of land, trying to get the same good ideas. I mean, the good news is we are competing in that sustainability and cooperating as much as we can. But when it comes down to that final piece, and to be able to share the heat with somebody, it's really difficult.
I just read an article on the desalination last night, as a matter of fact. You know, in California, the community there turned down the proposal for a desalination plant that would produce, 50 million gallons of water a day, right? So the community turned it down. So you can buy the land, but if they don't want something built, that's like you just said a minute, not my backyard, right? And we want to turn that into, bring it here because we want it. So, especially with the droughts in California, I just was surprised that they turned down something like that to produce that amount of water per day. That would help us, especially when Steve is talking about, water is a major component as we're trying to get these numbers down to where we need to be sustainable, right? Just that.
So there was a comment from Joseph McDonald that rang true with me, asking, just paraphrasing, Steve, he's at 1.026 ORNL, even in humid Tennessee, Frontier is going to be kind of 1.03. How do we transfer this domain knowledge to others, right? So lots of people are trying to do this. They're still stuck at 1.4, 1.5, 1.6. How do we as a community make this information available? Right, because if we're trying to build to a sustainable, ecosystem, helping others clearly has to be a part of that, right?
Yeah, I think perhaps, some sort of commoditization of liquid cooling, so that it's readily adopted for hyperscaler and Bitcoin mining and the other things that traditionally just have super cheap chips and a muffin fan front and back to move air across. Right? So if there was some better way to do a low cost, few pennies, I don't know, maybe it's 3D printed thermoplastic heat sink that's, profiled for the motherboard. So it just sits there, right? And then you do the heat sink, and then it's custom, but it's custom for that motherboard, but there's a million motherboards, right? That are filling these hyperscaler data centers, and then water's in and out. You could figure out the routing so that you cool the, in what way you want the water to flow through to pull this out, and then that heat exchange, or that thermoplastic heat sink is in itself something that's recyclable. But that's part of the building block. Then you improve density, you eliminate the fans, and you're not.
Can I put Mark on the spot? Mark, what are y'all doing about this exact problem of how do you get an effective heat transfer mechanism close to a server that only lasts 32, 36, 40 months?
Yeah, well, most of the industry is still working on air-cooled CPU systems, and it's definitely not the most efficient way of cooling. Like we mentioned, air is a good insulator, but we're being driven to liquid cooling systems by our customers, the ones that need the high performance compute, that where the only solutions are GPUs or TPUs, and being able to apply cooling either as direct on chip or immersion or things like that. You'll see, I think, Microsoft has made some announcements and has some production load running in both immersion cooling and on chip cold plate kind of stuff. But it's not clear to me that that's going to become a widespread solution for more than a decade. It's still the sort of general purpose computing is handled by the air-cooled computers. What I do think you'll see is continued movement to the more efficient data centers. A lot of the cloud growth, in my opinion, is due to companies looking at their own data centers running a 1.5 or 1.6 PUE, and then they look at Microsoft's at about 1.2, Google's at about 1.1. And they do a lift and shift kind of strategy. They say, I've got 1,000 computers in my data center. I want 1,000 virtual machines in your data center because you have lower operating overhead. We get a lot of efficiency gain just by the movement of IT resources from enterprise data centers to more efficient colos or more efficient hyperscale companies, where it's our business to make sure that we run them as efficiently as we can, right? That's both for our profit and for the competitive nature of the business, where customers are going to shop around for the cheapest operating costs they can get, and operating overhead, PUE, is a part of that. So I think market dynamics will drive it to a large extent, as much as anything else.
You mentioned the enterprise compute. That's one of the things we're trying to do here, at least I am, is trying to drive any of that enterprise compute to the cloud.
Yep.
Right?
Yep.
Get it out of these inefficient data centers and get it to the cloud, and just keep DOE, with our supercomputers, the HPCs and stuff, doing what they do best, right? And that's just one of my goals that I'm trying to do, to try to push. And because we do these quarterly data calls and we're looking at this data, and I see these, and I'm like, we got to get these moved. What can we do with the program offices and try to drive those into the cloud, right? And so that's what I'm trying to do.
Yeah. Yep.
Yeah.
And there's, like JD, if you look at it, there's no reason that anybody should be running an email system, right? An enterprise company or a government agency, because nobody's running one as efficient as Outlook or as Gmail or some of the other.
Right. And that's one of the things I was, you see me stand up, jumping up and down, but when we, DOE headquarters, we went with, I'm not trying to say vendor, but the fact is that we went to the cloud with our email, right? Try to get rid of those systems. As you saw heard from my bio, I used to be a systems engineer with, all this. So I was Microsoft certified, and I ran email systems, firewalls, and network operations, CCDA, and all that stuff. And to try moving that stuff to the cloud was where I saw we needed to get rid of these systems in here running this stuff, and they're going to be virtualize, move to the cloud, and be much more efficient. So, yeah, thanks, Mark.
Yeah, so we could bifurcate the discussion, right? Because there are lots of advantages for the enterprise side, right? But if we change this to a panel on, on-prem versus cloud HPC, right, it's going to become a death match. So
sorry.
Yeah, right. I mean, so it's kind of fun,
let's
right?
do that. Let's do that a little bit, though, right?
Yeah.
So,
If you pry that, you're going to have to pry it out of my dead cold hands, right? So
or
not going to let you do that in the
give
cloud.
you a compelling reason to do it, right? And
Please do. This
is
is
not a compelling reason, right? But there is high performance computing available in the clouds, and not for like you are the experts. I mean, you are your product in essence is computing, and so it makes sense that you're the best at high performance computing in the world. We could probably never achieve that because we have to have some generality to it, but we can make high performance computing available to a lot wider audience. And do it more efficiently than they could do it, for example. Not as efficient as the best in the industry, but better than the average in the industry, I think, is where we would strive to be.
Well, I think there's a clear role for what the national labs do to sort of push that leading edge, to provide systems to solve problems that can't be solved anywhere else.
Right.
But if you're going to run, CAD programs, there's certainly a much broader level of the pyramid that fits really nicely in the cloud, and doing HPC in the cloud is an option, and it should be fully explored, right? So if you've got
then it's not HPC, right? I mean, running MATLAB on an Azure instance, that's not HPC to me, right? So
but running massively parallel molecular modeling, in an HPC on a cloud is probably right. And you've got a million processors, but we've got a billion, right? So even if we're not as efficient, then it's in essence infinite resource, and not every problem. Obviously not every problem scales to that point. You've got to have the special communications and the high performance.
Well, it doesn't even have to scale per se, but if you're doing parametric studies of things to explore a full design space, right? Those are the things that'll it's not using the full capability of Summit and Frontier for a single instance, but maybe there's 100 smaller instances that have to be run that don't need this single large cluster. And
so you're talking about vast ensembles.
Exactly.
They're actually smaller components.
Yeah. Instead of saying, this is what I'd like to do, how's it going to work? It's, I need to do this. Can I optimize it? Right? What's the best configuration? What's the materials by design? What's the chemical configuration? What are the bonds? Right? So you're asking, this is the material. This is what it's got to do. What is the molecular design that's going to meet that best? Those are the kinds of things that will fit. In the cloud. There's a market for it. There's availability, and I applaud both. Right? And we're doing both efficiently.
Yeah.
As an
the other
industry.
thing that we frankly are very envious about is the utilization of HPC. You guys have jobs stacked waiting to run, and are trying to keep those things running at 98% utilization. That's envious. We're envious of that, to be able to. There was earlier discussion about idle computing and energy use and things like that. And
we don't know what that is. I mean, it's a Tetris game at some point, right? You're just stacking jobs in and trying to have an agreeable throughput of your workload.
And in essence, that's what cloud is, right? We're trying to aggregate disassociated jobs that customers have onto shared hardware. But there's nowhere near the efficiency that there is in the high performance computing world right now.
Right.
But maybe we can learn, maybe we can exchange ideas and techniques, and be able to get better scheduling and better efficiency, because utilization is one of the biggest levers that we have in terms of efficiency, both in high performance computing and in cloud computing.
Yeah,
Yeah,
this whole thing reminds me, right, Steve, you're probably familiar with Clayton Christensen's comments about how the U.S., basically lost steel to, lost the steel industry because they were concentrating only on the upper end, highest margin of the, places like NREL, places like Oak Ridge could literally be facing exactly that same challenge that Clayton Christensen talked about in terms of cars and steel and a lot of different industries.
exactly.
So pretty cool.
So
All right.
if I,
So
we
got a couple of
much time
minutes,
do we
and
have
then
left?
Sid's gonna cut us off hard in about 2
Okay.
minutes. Are there questions in the chat that we would like to hit?
I could go into the gaming PUE one, but it would be a passion play more than a. So sorry, Herb, but yeah, we could talk outside. It's a well-beaten horse.
So one comment I'd like to make, because it came up a couple times during David's talk earlier, that the machine learning for efficiency, I don't see a lot of that, but from an operational improvement, right? It's been a little while, but every time we had an issue with fans or a cavitating pump or something, if we had been smarter about the data, right, we could have changed a outage to a service call, right? We could have routed around, we could have done something if we had been smart enough in how we monitored and been able to do some form of anomaly detection. So that's clearly an operational improvement. It's not an efficiency improvement, but just to be able to detect anomalous behavior. And there's lots of ways to do that, but collecting lots of data is a good start, and then being able to monitor that. But it's sometimes the improvements are there in the efficiency. You'll find something, but it's often something is you're more or less finding something that's not working as it should be, rather than improving the efficiency of something that's operating within its normal limits.
All right, if you don't mind, I've got one more comment that it's almost intentionally going to lead to subsequent discussion outside of the panel today, and it was mentioned, it was a question to John Schauf that I also had about, we're chasing all of these smaller dependencies and trying to optimize all these different variables. For decades, the application efficiency just continues to be single digit terrible, right? So when we're talking about sustainability and other things, do we really, why aren't we focusing more on that? Why am I still running, a million lines of Fortran that gets 2.5% of the peak performance of the machine, right? Instead of, why am I still doing that?
So my opinion is that software engineers are the scarcest resource in the world. It's much easier to throw hardware at the problem than it is to find software engineers that are capable and interested in working on that kind of plumbing that makes things run really fast. And that is a skill set that we need to really build as an industry.
That's a really good point. All right, any final thoughts from JD or Steve, and then Sid's going to cut us off.
I just like to comment about the PUE family and water usage and the carbon footprints. As we move forward and we're making these fractional things, when I look at data center optimization initiative, and when we really want to see how efficient a data center, we need to look at all these things, not just PUE, right? How efficient is this data center? Look at the PUE family with the carbon and the water usage and all that. Take it all in its totality, not just one little single out PUE by itself. That's my final thought.
Yeah, I think PUE is sort of like LINPACK, right? It's an indicator, it's a performance indicator. It's not the be all end all. And it helps. I'm more interested in waste heat reuse. I think there's huge opportunities there, but not if you're going to optimize and put your data center out in an isolated location. And longer term, it's the e-waste. I think those are bigger opportunities than trying to shave another 100th of a point off of your PUE.
Agree. Yeah. And I'll just finish by saying that I think that, having a focus on carbon is really going to be important. With IPCC saying now we got to start thinking about pulling carbon out of the air. Maybe there's opportunities for the IT industry to look at things. I mean, one of the things you need to be able to take carbon out of the air is air moving. And hey, we move a lot of air as an industry. So maybe that's something that we can look at as different ways to contribute to that carbon reduction technologies overall. You're on mute, Jim.
Jim, you're muted. Your sage thoughts
Yeah,
were
sorry. So I was trying to be good so you don't hear typing. To the three panelists today, thank y'all. I can't wait to find an opportunity to have a beer with all three of you. That was great. I'm sure Dave Martinez will join just because there'll be beer there. And then he's got and as a matter of fact, Dave Martinez is going to be leading a session on liquid cooling right after this. So I'll be very interested in that as well. Sid, thank you so much. And
thank you.
And actually, thanks to the 100 people watching that, right? So there were some great comments in the chat. So
yeah, lots of great ones. Good point.
Yeah, thank you so much.
Yep. Thanks all. Thanks, Jim, Steve, JD, and Mark. Okay, a final session for the day. A discussion panel on liquid cooling being driven by David Martinez and panelists David Masuda, David Grant, and Steve Harrington. Thanks all for joining. Over to you, David.
Okay, thank you. Oh, and thank you for the young picture of me. That's really generous. Let me share my screen. Okay, let's see. All right. Did everybody see that?
Yep, we do.
All right, perfect. All right, this panel is going to talk about liquid cooling. And what I did is I comprised a bunch of different questions that I've had over the years, and even working through the field right now, they're living it every day, some of the questions that we have for liquid cooling. For some of the novice and some of the experts as well. So I have a great panel here. I'd like to introduce Sammy Zimmerman first. Sammy, please tell us a little bit about yourself if you're online.
Yeah, I'm here. Thanks, Dave. So Sammy Zimmerman, I'm a senior product manager with NVIDIA. My background is in liquid cooling and thermal engineering. So worked a lot with Dave. Happy to be on the panel.
Yeah, that's great. Yeah, Sammy's, me and him have teamed up for many seasons, working at NREL, setting the very first Apollo system on board, a great expert. Next would be David Grant from Oak Ridge.
Hello, I'm David Grant, a mechanical engineer with Oak Ridge National Laboratory. Been here since 2009. I'm involved with the design, construction, and operations of the mechanical systems that support our data centers. And I've been involved with the different system iterations that we've had here. I've seen Jaguar go to Titan, and then I've seen Summit come online, and now we're seeing Frontier come online, and been intimately involved with the liquid cooled side of things, and have a really kind of focus and interest in the controls aspects of these of these cooling systems that are having to support these very large HPC systems.
Yeah, David Grant and myself have written a few papers, and we've worked together combating solutions in the cooling area and some control systems as well. Next is Steve Harrington.
Hello, I'm Steve Harrington. I'm the proprietor and founder of Childyne. I got my start in liquid cooling when I realized the PUE was about 2 for everybody, and that was horrifying as an aerospace engineer to realize that people are wasting so much energy. So we set up Childyne. We have a couple of systems running at Sandia right now, and a couple more systems in South Korea. I think the background that I have in thermodynamics and teaching students how to build and fly liquid fueled rockets at the university. Really helped liquid cooling, along with owning a boat since I was 20 and, and always having to fix it. You get a real good respect for leaks and corrosion.
Perfect. Yeah, I've worked with Steve for many years. We've did a few presentations back in the day on liquid cooling, and a great champion of liquid cooling. The next is David Masuda.
Hey, good morning, everybody. Yeah, my name is David Masuda. I'm with ChemTreat out of the Bay Area, and I've got almost coming up on about 20 years of industrial water treatment experience, specifically here in the Silicon Valley. Grew up in microelectronics and data centers. So I've had the opportunity to experience and participate in the growth and maturity of liquid cooling in data centers. And currently I support the water treatment needs for Lawrence Livermore National Labs in Livermore.
Perfect. Yeah, David is highly recommended in the water treatment area, which is, if you're doing any type of liquid cooling, you know how critical that is. It's just as critical as any component in the system. All right, here we go. These are what I call my superheroes of liquid cooling for right now. I mean, there's plenty of us out there, but this is the ones that on our liquid cooling planet that I think we'll be talking at. So I'm going to go through a few of these questions here, and I'll ask specifically a few of you to comment, but please all feel free to comment. So first, I'd like to start with major differences in air versus liquid cooling, supporting infrastructure and benefits. So David Grant, please.
Yes, so as I mentioned, I've seen many different systems come online here, and so kind of walking you through what we've seen we've seen you know, the strictly air-cooled racks that would pull 3,000 to 6,000 CFM directly from the floor, and it's surrounded by perimeter crack units or crawl units. And the main difference that we've seen as things progress are to the facilities is, you know, the infrastructure, more infrastructure has to go out onto the data center floor, and the floor loading and structural requirements for these liquid cooled racks, especially when you have multiple larger systems, gets pretty serious. So from a mechanical standpoint, some of these systems are pulling in, they still have a data center airside component in some cases, and then some are basically sealed hot boxes. And so we try to customize the mechanical cooling systems based on those individual rack needs. And but ultimately, we're bringing water out onto the data center floor, whether it's under a raised floor, or we have several iterations where we've had to do slab on grade construction and actually bring the water out over the top of everything. Overall, from a constructability standpoint, we look at our basic availability of labor and that type of thing to try to optimize who does what and where. Sometimes we try to leverage getting things built off site and bringing them in and bolting them up together within the data center, while in other instances it makes sense to go ahead and put, you know, your pipe fitters or whatnot there on the data center floor to make those final connections. But largely the expense with these liquid cooled systems, we have seen those go up because we are having to install additional infrastructure to get out on the data center floor. But the performance is there. The little problems that you have with air cooled systems, where the airflow management both inside the rack and outside the rack are critical to being able to actually cool all the components within the rack. That largely is alleviated with these liquid cooled systems, to where the components are a lot more happy out there and operating at those more elevated temperatures.
Good. That's good. That he's correct on a lot of that. I mean, when you're in the transitional phase and you're looking at you're air cooled and you're turning to liquid cooled, then you're going to have to have a transitional phase where you have a lot of air cooling systems along with liquid cooling, and there's a lot of challenges there. Sam, anything on this? You might be on mute, Sam. I'm not sure. Or maybe you don't have anything on it. David Masuda, any comments?
No, I don't have any comments to add to what David already mentioned.
Thank you. Okay, let's go to the next one. Are liquid cooling systems too complex? The infrastructure and controls. David Grant, this is your area right here.
Okay. So these large systems come in from the manufacturer with prescribed envelopes for temperature excursions and magnitude and duration. And with the very large systems, it is challenging to have your system respond and stage up appropriately while keeping supply temperatures within a stability criteria that's given. So when we progressed from the cooler water temperatures that were supported with chillers, and we've progressed over to the cooling tower only chillerless cooling systems, there were a lot of conversations during the design where people would say, oh, it's just a bunch of pumps and heat exchangers and cooling towers. And that is true, but being able to stage on all these different pieces of equipment at the right time and maintain the stable temperature can be a challenge. With these larger systems, we're seeing 10 plus megawatt load swings within seconds, and with those types of load swings, you got to have your control system finely tuned. So we spend a lot of time putting in the engineering tuning parameters that we feel we're going to need down the road in order to tweak things while in operation.
Yeah, it can be very difficult when you're managing or trying to manage these large systems, and when you're trying to write a sequence of controls, a lot of if-and statements, there's a lot of different parameters that you need to include in this that you didn't think you had to in the past, and most of it can only be simulated because you really don't have anything to do a practical test on or commission. Once you're in operation, it's almost the commissioning phase, if you will. I mean, you could do it on a small scale, but when you have a larger scale and you're moving lots of water, moving large pipes, and whether they be pneumatic or electronic controlled, and the reaction time on it, your slope intercept, all of that comes into play. It's very, very difficult thing to manage. Anybody else have any comments on that?
So Dave, when we did our first installation at a government lab in South Korea, the salesman did the facility water system, and basically he just put a cooling tower in the parking lot, and we hooked up our liquid cooling system to the cooling tower. We just dealt with whatever temperature it was, 2 degrees C in the wintertime and 35 degrees C in the summertime, and it worked okay. The CDU controlled the temperature to the servers, so they didn't get too cold and undergo condensation. But I think it was, from the data center operator's perspective, it was just a little too hairy to be running directly off of cooling tower water. Because at least once they had a problem where the nearby trees started blooming and all the flowers fell in the cooling tower and clogged things up. So there's the way that you and David Grant and the DoD are doing it, which is obviously the right way. But you can also get away with being a little bit hack and still have a reliable system.
Yeah, I mean, that's a little more in the Fred Flintstone area and not the George Jetson. So I got you there. I mean, I've been to many sites that were somewhat similar and they believe an open loop system is the way to go, but we need to probably tune it up a little bit, go open closed loop or something like that. But great comments.
Hey, Dave, this is Sam.
Hey, Sam.
Sorry, I was having some IT problems on the
Welcome
on the
back,
last
buddy.
one, but that's all right. I don't think that it's a problem with liquid cooling systems being too complex. In some ways, we want them to become more complex in that they take inputs from the cluster in the long term, and so that they can become more efficient. They just need to be easy to operate. And then from a vendor point of view, right, whether it's silicon vendor or the OEMs, right, we need to continually do a better job of making it simple for the end customer to attach to their data center, right, and not have to upgrade their data center with each new cluster.
Yes.
So I think there's a lot of things that we can do to make it even easier from a data center perspective, but I also think there's a lot of things we should be doing to make them more complex in terms of the controls, where they become more efficient and they take more inputs from the cluster itself.
Yeah, I totally agree on that. I mean, using your AI or machine learning, so basically the machine would cue the system when to run, and that way you could find the optimum curves for everything. Place a large job at the optimum time that there's the most cooling, and be a little more proactive in the way you schedule your jobs based on all the inputs and all the variables. Good stuff. So here we go. Next question: process warm water versus cool water entering temperatures. W1, 2, and 3, 4 water. Comments. Let's David M., do you have anything on this?
Well, from a water treatment standpoint, entering temperatures, aren't a big concern for us. When we're looking at the water and protecting the system, we're looking at three things: microbiological growth, corrosion, and deposition. And the entering temperature is not so much of a concern as the overall bulk water temperature of a system. And obviously for us, there are benefits to keeping the temperatures lower where it's feasible. But it's really, you're going to have a lot of variability due to the fact that the skin temperatures locally on your heat exchangers, can be 10, 20, 30 C higher delta than what the bulk water temperature is. So, higher temperatures can also drive corrosion at a faster rate. So there's some influence there, but it's not going to be on a well-treated system significant enough that you're going to see any adverse effects during the lifetime of a system. So not really. I don't have any key insights as far as process temperatures. So
the key though, I pick up on a key point that you said, well-treated systems. So you need to make sure as you move to these warmer waters that you need to keep an eye on your the consistency of your water by sampling or whatever the case may be.
That's a fair point. Yes.
Steve, Sam, you guys have any comments here?
I think that with warmer water, it's great, but you need to consider the lower case temperatures that are coming up from some of the new CPUs and GPUs and so on. And you may end up having to flow so much water over the chip to keep it at its case temperature specification that the efficiency of your liquid cooling system degrades as you have more pumping power, and also the chip itself will use up a little bit more power as it gets warm due to leakage current internal to the chip, and that can be 5 or 10% depending on the exact model of the chip. So when you're designing these systems, it's good to think about all the effects, not just, wow, warmer water is going to be great for whatever reason I'm going to use it for, but but you need to think about the costs of warmer water as well.
Sam.
Yeah, no, I think that's right. I will say, pumping power is small compared to efficiencies that are gained within the chip in terms of just performance per watt, right? If you can get that additional performance, then the pumping power is small, right? But it needs to be looked at, on a data center by data center, cluster by cluster case, right? So that you can get that right balance. Because going to warmer and warmer water just for the sake of going to warmer water isn't always, it might produce a better data center metric, but in terms of just performance per watt, you're really doing yourself no favor, and a lot of times you're doing yourself harm. So I think we have to be careful about just continuing to increase the data center water temperature.
So yeah, so looking at data center build out for people that are building out or trying to get into liquid cooling or in the process of it. So maybe a process loop system that has flexibility built into it. David, can you tell us how you're doing it over there?
Yeah, so with the prospect of needing colder temperatures, now that we've gone through the iteration of chillers and we've made the step towards cooling towers, and some of these chips that are coming down the road may need something in between. And for some of the support racks that we've stood up recently, we've been able to stand up a trim system that can actually pull in our economized water as well as chill water, and provide the temperature that those specific racks need within the piping system that's within the data center floor. But for looking way down the road for other future systems that potentially need colder water, it's a big challenge to have to get those temperatures where you need them on the data center floor, because ideally you're still sending the warmest water possible to the other systems that could use the warmer water. But on a facility by facility basis, it may be easier to provide that trim function outside of the room and send it to the whole space. But there's an energy compromise to that, that we're weighing that constantly as we see the potential for future systems. And then if you go beyond that and try to surgically provide those cooler temperatures, there's a big facility challenge, because now you're putting additional infrastructure out on the data center floor to surgically get that cooler water where it needs to be. But there is those we're constantly weighing those the energy efficiency of the entire system versus catering to this one canary in the data center. So it's a really that one is going to be on our minds for the next many years.
Yeah, I totally agree. So it's back in the day when we air cooled, it's like herding cats, right? Trying to get the air where you need it to be. But now we have liquid cooling, and now we're moving forward or to warmer water. We're going to get heat reuse, et cetera, et cetera. But now there are some systems, just like you said, that are not wanting that warmer water. So it's a system within a system that we have to start looking to manage. Okay, we'll go to the next one. Corrosion prevention. Long-term closed loop coolant use. How do we prevent degradation of performance, breakdown of fluids, the consistency within the fluid? How should you testing be done, and when should the coolant be flushed? David M., man, you're the man here.
All right. This is there's a couple of questions that I think are being asked here. So I'm going to start at the 10,000 foot view, and then we can get more granular. So when it comes to corrosion prevention, there's the three components that I mentioned that we are concerned about: microbiological growth, deposition, and then the corrosivity of the water. And all three of those things, microbiological growth and deposition, also can contribute to corrosion. So we're really concerned about making sure that we, from a water treatment standpoint, are monitoring and proactively minimizing the potential for all of these things. Water is a universal solvent, and so it will cause corrosion over time. We cannot stop it, but we can do a lot of things to slow it down. So in terms of coolant in the coolant and how do we prevent degradation of performance, what we're looking at and kind of a high level recommendation that we start with is, use good quality water. And good quality water starts with water that is, has a high level of filtration to remove suspended solids, water that's potentially been softened or deionized or RO to clean up the water if it's water with high levels of iron or other inorganics that might contribute to corrosion or organic biological growth. So you want to start with clean water. That's kind of priority number one. Then typically what we do in putting together a program is evaluate the metallurgy of the system so that we know what metals we're trying to protect. The common metals that we're going to run into on the systems that we deal with are going to be copper. You're going to find those in most all of the heat exchangers. And then, various metallurgies for the transmission piping. And transmission piping, we'll see carbon steel, we'll see stainless steel, we'll see plastics. So it just kind of depends there. Once you determine what metallurgy you have in the system and what you need to protect, then there's a number of companies out there that offer inorganic corrosion inhibitors. And it's really important to look towards inorganic solutions. A couple of examples of inorganic corrosion inhibitors are molybdate for steel and azoles for copper corrosion. Inorganic is really important because organic corrosion inhibitors can break down and also can be consumed by microbiological activity, whereas the inorganic inhibitors tend to not break down, and so they'll last as long as the system is running, as long as we're not losing water. So that's kind of step one, is to make sure, or step two is to make sure we've got the right inorganic corrosion inhibitors in place. And then typically we also are going to pair the inorganic corrosion inhibitor with a biocide. Typically when you start up a system, you're going to have some level of microbiological growth. That's just a function of, the installation of the systems, fresh water coming in. And so there's some steps that you're going to want to take to disinfect. And so there are industry best practice standards on how to do that. There's a couple of different tools that you can use. The most common one is to use a non-oxidizing biocide and slug feed it to the system upon commissioning. So once you've got the corrosion under control and you've got the microbiological under control, and you've cleaned the water to the point where you're not concerned about deposition, then the next step is the testing and the monitoring, right? At this point, you really shouldn't need to flush the system unless you have some type of upset or interruption that's unforeseen. So assuming that you keep the system running and it's in good standing, you ought to be able to then just start working towards the monitoring and control side of the program. When it comes to monitoring, typically routine monitoring, we recommend once a month sampling of the system. And the things that we're looking for in the samples are going to be specifically our corrosion inhibitor levels to make sure that those are in good range. We're going to be looking at metals levels. So we're going to be looking at iron, copper, and aluminum primarily, because of the concern that if we have a high level of, let's say, copper floating around in the system, that copper can then land on your carbon steel piping and cause galvanic corrosion. So we want to minimize that. And then we're going to monitor the bio levels in the system. So we want to monitor those typically on a monthly basis. And one of the learnings that we've had over the last couple of years at Lawrence Livermore National Labs is that if you have a closed loop or an open loop system that's tied into, racks of servers and different systems, what you might see in the bulk water. So when I say bulk water, I mean, the main transmission lines in the system may vary greatly from what you actually are seeing at the racks. And the reason why is because the skin temperatures in the racks, as well as the flow and the diameter of the transmission piping, can be very different. So one of the learnings that we've had at Lawrence Livermore National Labs is that if you have systems where you have a high variability in the design and the operation of your water liquid cooling through the rack versus in the open system, which these days probably the majority of the systems have, then it really behooves you to not only monitor the bulk water, but also monitor and take readings at the racks and take samples at the racks. That can get you out of a lot of trouble in the long run, because what you might not catch in the bulk water, you may catch in the racks. And I would even go as far as to recommend that if it's feasible to have a monitoring server or a monitoring rack that's set up just for the purpose of sampling, that is operated under similar conditions to the entire rack, that would be a great improvement from a water treatment monitoring standpoint.
That's something to simulate the heat that the rack is facing and the low flow versus the larger processed waters delivering to the CDUs. Good,
Correct.
good stuff. Anybody else have any comments here?
Well, one thing that I think needs to come into this is the human factor, because in the past with our installation in South Korea, they decided that they weren't going to run any coolant additive because their water coming out of the tap was 50 TDS. And that worked okay for about a year until it started clogging up with algae. So, whenever you think about, deploying liquid cooling widely to, locations all over the globe, not just DOE data centers with people who are really smart about liquid cooling, is you got to think about how we're going to deal with users who aren't familiar with liquid cooling and maybe may not follow directions as like David Masuda just mentioned about what to do and how to deal with that, because even if the liquid cooling, if the customer doesn't follow the instructions, you still have to recover and make everything work again.
That's correct. Good stuff. Yeah, so I'm going to combine the next two questions together. They don't go hand in hand, but the glycol in the cooling system, is this necessary? If so, what is the benefit? And then we'll go right into leak prevention. Is this a problem in liquid cool systems? So David Masuda again on the glycol, and then David Grant, some comments, please.
Sure. So glycol in cooling systems, in my experience, glycol is fed to a cooling system to depress the freeze point. And so if there are concerns around, the climate, where you're in a cold climate, and so you risk, during the wintertime pipes freezing, then you can add glycol to depress the freeze point. The other reason that we see glycol added to closed loop systems and data center, infrastructure would be if they're looking to achieve lower temperatures that are, below 0 degrees Celsius. So if you're trying to get cooling below 0 C, then you can add glycol to achieve that. So it can be necessary depending on the climate or the application. The benefits for glycol are the obvious ones that I just mentioned. The other real big benefit for glycol in a system is that if you keep your glycol levels of elevated above 25% by volume in the system, that creates a biostatic environment. And what I mean by that is that that water becomes too toxic for microbiological growth. So glycol can be a real good ally in terms of keeping microbiological growth static and not allowing microbiota to grow in the system. Now the catch is that if the glycol levels dip below 25% and really below probably like 20%, then you get the adverse reaction where now that glycol can actually become food for bacteria and they will then start to thrive. So it's kind of a fine line where if you're gonna do it, you need to make sure that you keep it above 25% minimum. So meaning like if you're looking for a freeze point that's just slightly below 0C and you only need 13% glycol to get there, you really need to just say, hey, we're gonna take it all the way up above 25.
Good points. Great point on that, because yeah, I'm not a huge fan of glycol myself, but that's just a personal, I'm just not a big fan of it in a liquid cool system. Especially to your point, I'm glad you mentioned that, because you think you have a fail safe for the bacteria, but then all of a sudden, if you're not watching it, now you have food for it. So that's a great point, and I'm glad you made that.
Yeah.
David Grant.
Yes. So real quick on the glycol, from my experience, we actually don't have any glycol in any of our cooling loops. So just a quick note on that. On the leak prevention, we have had really good luck without having leaks. Summit, has over 100,000 wetted connections in it, and its distribution piping is overhead with hoses and quick connects and even some hand tightened valve bodies. And we haven't had any issue. Typically with these systems, with our large systems, we have active makeup because our probability of a catastrophic leak is pretty low. And we have 24/7 operations, so we could get in and address things quickly if we needed to. For our smaller isolated small loop systems, they typically have fill tanks that can provide a limited amount of water to them. And in those cases, we have spot detectors and onboard leak detection that's inside of it. For Summit, we ran leak detection cable. Since it's a slab on grade, we actually ran leak detection cable underneath the rear door heat exchanger part of it to get that coverage within that data center. And we usually have the system level rope and then individual pieces of equipment may have spot detectors. But overall, we haven't had any problems with leak beyond the occasional maybe Schrader valve on a rear door heat exchanger weeped a little bit, or maybe a quick connect weeped a little bit, and usually they get reset and then they're good to go.
Do you have on your system when you make up water, is it an alarm point? So basically, if you had a leak and a valve open, so you would send an alarm to your whoever monitors your alarm as a level X alarm.
Correct. And
nice.
If it's accompanied by a leak detection alarm from a specific area in a specific place, then they know exactly where to go to address it.
Kind of an if-and statement. If this and that, then you better get over there with a mop and hurry up.
Right.
Sam.
And we
I'm sorry.
One more quick note. Since we have stacked data centers, we have first floor and second floor data centers. We did spend quite a bit of time going through and sealing everything on the second floor so that nothing on the second floor impacts anything on the first floor.
Oh, so you get a mop and an umbrella if you have a leak. Just kidding. Sam?
Yeah, let me hit the glycol one first, just real quickly. Most of us are used to thinking about large supercomputing systems, right? And the larger the system, the more we can add water on site and treat water on site and do things like that. But one of the things that I like to say is that the real goal in reducing carbon footprints of data centers is to get down into the smaller clusters, the enterprise type clusters, and turn more of the world's data centers into liquid cooled data centers, not just the large supercomputing centers. And glycol can actually be a really good tool to help us do that, because for smaller clusters, you can actually, it's a lot easier to ship, you can pre-fill, you can do a lot of things in the factory before it gets to the data center for these customers that maybe don't have all of the expertise and the manpower on the data center side that maybe some of the labs have. So I think that's another thing to think about with glycol is what's the size of your cluster and you know, what's your end customer.
That's a good point. And so then it would be a minimum percentage of glycol.
Yeah.
Yeah, perfect.
Yeah.
Nice.
And then on the leak prevention, let me just touch on that real quick. We end up talking when we get into leak detection a lot about, or I'm sorry, leak prevention. We end up actually talking about leak detection and leak mitigation, and that's all really important. But there's no water system in our house, our buildings, anywhere else where we would tolerate the idea of a leak, right? And leak prevention really needs to start at the design of the system, the cooling loop on the node. And we need to continually do a better job of making sure that there's no leaks to worry about, right? As opposed to just jumping directly to leak detection and leak mitigation, which I think we tend to do as an industry too often. So we need a lot more robust designs on the to prevent the leaks to begin with.
That's a great point. Yeah, I mean, do it right first so you don't have to worry about it. That's a good point. Steve?
Okay, I have a couple thoughts on this. First of all, I prefer water over glycol. Our system works better with it, and it conducts heat better. As far as the leak detection and prevention, I think the issue is you know, for instance, the systems at Sandia, you know, there's 6,000 connections there, and sooner or later something's going to break or get clogged. And if you think about your home system, you don't really have, except maybe, well, you don't really have a system at your home where you're connecting and disconnecting every day. And at a data center, you're connecting and disconnecting the server every day as you have to replace RAM chips or whatever. So I think that, you know, obviously our solution, which is to run everything under negative pressure. So when it does leak, it sucks air into the system instead of leaking water onto the server. You know, we like that better because we just figure with that many connections, you're going to have a leak. And if you've ever been in an older airplane, you know that obviously there's always leaks. So, you know, I think that we're going to have to live with them. And our solution is just run under negative pressure so it doesn't leak water out.
Good point. So I'm just going to go to the last question because I think this is a really important one. Who will maintain these liquid cool systems? Facilities, system admins? I mean, so we're building all these liquid cool systems and we have expertise in different areas. So we have our facilities guys, we have plumbers, you have our reefer guys, refrigeration, and then we have our engineers, and now we have our sysadmins. So just a question out there, who's going to maintain these in the future? I'll start with David Grant.
So it's a really good question. Our approach largely is you know, a integrated design. Well, we have an integrated design factor, but we kind of integrate on the operations side too. So the folks that are on the engineering teams for the design and construction help with technical aspects of the operations side. And so we're ultimately trying to, in our case, in the national lab cases, we're trying to stand up the missions of DOE. And so everyone has an interest in to that end. And so usually when a problem arises, there'll be an assessment, and then the team will come together and decide the best way forward, depending on the problem.
Sammy, what have you seen out there?
Yeah, I don't know that I really have a stance on who should maintain these. I think that's for folks who are working more in the data center now.
Okay. I mean, they're going to have a certain skill set, right? I mean, they're just not going to be able to, because some of these systems with their CDUs, negative pressure or just plates or even immersion, there's a little bit to each one of them, right? I mean, it's not like you can walk right in and take it over. So there's with the power densities and stuff. So there's a little what we call the fear factor for some people.
Yeah, actually, I think that's a good point, Dave. And I think, quite a while ago when I worked for an OEM, right, kind of the first approach from the OEM perspective is to send the person out there that does all the other maintenance on the cluster. And you do need a special skill set and somebody who's used to replacing DMs and replacing hard drives, things like that. And now all of a sudden you're asking them to do maintenance on a CDU or something like that. They're kind of lost. And so we do need to make sure that we have the right skill sets in the data center. We do a lot more training to maintain these.
Training.
Yep. Yeah.
Anybody else? David or Steve?
I have a real solid idea here, and that is all the auto mechanics that are unemployed when we switch to electric cars. They already know how to deal with computers and plumbing.
We just go from this to reset customer feedback.
Yeah.
Exactly.
So,
David M., have you seen anything out there that leads you to believe that there's this could be a problem?
Whatever.
What I see in industry,
whatever, 2 hours.
all right. So what I see in industry is that the folks that have the most success are the ones that have a mechanically inclined skill set, person on their team that's involved in the maintenance. Growing up in the data centers here in the Silicon Valley, the classic scenario is that they open up a data center and it's filled with employees who have an electrical skill set or an IT skill set. And to everyone else's point, Steve's point and David's point and Sammy's points, having someone who has the appropriate skill set to do the maintenance and the monitoring will lead to a higher probability of success in maintaining the program. So I think it's imperative to identify someone on the team within the facility that has or can develop that skill set and let them be the one that's going to maintain the system.
That's great. I think that's pretty much it for right now. I think we could do some questions. I don't know. What time do we have? Is it getting close to the end?
You're actually out of time.
We're out of time. Okay. Well, sorry, everyone with questions. we could send them to, I think, Natalie. Well, we got a couple of, okay. Does anybody have any outstanding questions they want to just chime up and talk to the panel about? Don't be afraid to be scared. Talking to superheroes here.
yeah, plus tomorrow we have a discussion group on liquid cooling.
Oh, right on.
And a discussion group on sustainability and on energy efficient software and on operational data analytics. So 4 very exciting discussion groups tomorrow.
Yep. To cut yourself in 4 quarters and go to each one of them. Sound pretty interesting, Natalie. I want to take time out really quick to thank the panelists, David Grant, Dave Masuda, Sammy, and Steve Harrington. You guys did a great job, and I thank you very much. I've worked with these guys in the past. David, I haven't worked with Masuda in the past, but I'm fixing to start working with you. I need some expertise in that area, and I need to learn. I mean, I did water treatment back in the day, but my knowledge is way just water towers and chillers. But it's been great talking with you guys. I work with you guys, and I look for some future collaborations with each and every one of you. And once again, big thanks to Natalie for putting this workshop together and this panel session. She does a lot for this organization, and I'm very happy to be a part of it.
Thank you so much, Dave, and thanks to all the panelists. Really appreciate your time. Folks, before we adjourn, just a quick note. So there is a different meeting link for tomorrow, and note the start time. It starts 1 hour later than the slot that it started today at. And as Natalie pointed out, we'll have breakout sessions. Please do convene at the top of the hour so that we could start at the right time, and then quickly split into different breakout rooms, virtual breakout rooms, that is. And then we will have lessons learned from each of these individual breakout sessions. The hope is leads from each of these sessions would come back, and then we would all aggregate in the same common room and get a quick recap of what happened in each of these sessions, right? So that would be an exciting session. And then the day will end with, the event will end with Natalie giving a quick overview of the working group and its charter and really its ongoing efforts within the community. And with that, once again, to reiterate, thanks to everyone, special thanks to the audience and also the workshop committee, right? There's a list here. Plenty of effort and collaboration went to making this happen, towards making this happen. Presentations, recordings should be on the website in a matter of days. And then for contact, please, as always, contact Natalie Bates, co-chair of the HPC Working Group. With that, thank you very much. Hopefully I'll see you all tomorrow. Thanks all. Bye.
Thanks, everybody.